Okay, I'm calling the meeting to order, wastewater treatment plant contingency committee. Today is October 23rd, and we have a quorum. On the committee is Bob Heffernan, Earl Webb, myself, Barbara Curtis, Mark Prouty, Tim Ritzert for the city, Austin Calaman, general manager at the of the BPW, and our guest, Hans Medlars, and Sharon are do everything at BPW. Hans is with Sussex County.
Sharon, only 8 years you can get a license.
I know.
Okay, so we've invited Aqua Nereda, Aqua Aerobic, and EnviRep here to talk to us about the Aqua Nereda system, with the understanding that it's if we can't reach agreement with the county, or even if we do and the county decides to try something innovative, this may be a technology that Hans has given me the eye. This may be a technology that we might choose. So now I will turn it over to Paula Dorn.
Thank you, Barbara. Yep, I'm Paula Dorn. I'm a process engineer with Aqua Aerobic Systems. Excited to meet with you all today. We were able to get a nice tour of the plant by Jeff and Austin before we came here. So saw the MDR system running, what kind of you're working with out there. I think it sounds like there's a lot of ideas that have been floating around, and there's a little bit of a history behind this. And you guys have, seen the effort that those membranes take, and you guys are planning for a capacity increase and maybe more stringent limits in the future. So here today to introduce you to the Aqua Nereda aerobic granular sludge technology. I know there are a number of questions, Barbara, you sent along. I may not hit everything in here. Please feel free to ask questions as I go through if you're okay with that, or we can save them ask them as I go through. I like the conversation kind of side of things. I don't have a slide for every question you had, but whatever I don't get to, we can certainly, address at the end, and I can try to get you what I can. Otherwise, I can certainly follow up with information as well. All right. So getting started off, I should turn this on first. Uh-oh, out of battery? No. Or am I pointing at the right location? Uh-oh. That's out first. I might have to. All right. Are you gonna do here's a wireless remote or mouse. I should have tested out. We were sitting here for like 20 minutes. Didn't even think about it. I have a laser going, so. Oh, perfect. Okay. All right. Thank you. Sorry, guys. All right. So presentation outline, just a little bit of a background as where the technology came from. I know we were just kind of discussing it a little bit. Then we'll move into what the technology actually is, a little bit about aerobic granular sludge, and then Nereda itself, how it scales up. Right there. We'll learn where the granules come from. Actually, you should grab them from my bag. I'll pass those around. I don't know. We can also look at the aqueduct tertiary filtration as well. I'm not sure if that's needed for you guys, but to polish up, so we can talk about that. I actually have those slides moved to the end. Major advantages, which we'll hit a little bit on operations side of things as well. System startup. So we can, again, I think more on operations side of things, what you guys would expect if you start a plant up. And then I do have your design in here as well that we had provided. So we can discuss that if you'd like, and they will change as time goes on. Right there, it seems to really like it, just right there. So this technology is not new by any means. It actually was started to be developed in the lab 30 years ago. If you're a wastewater nerd, this is Professor Mark van Loostrecht of Delft University in the Netherlands. He's the brilliant mind behind Animox, which is a sort of a shortcut means of nitrogen removal. But it's actually, this started off born out of anaerobic granules. So they wanted to see if they could do this on the aerobic side of treatment. And they were able to. It did take a few years. And I think Mark won the bet with another professor, which means he got a few beers at an Oktoberfest that year. And then they partnered with Royal Haskoning, DHV, which is an engineering conglomerate, again, based out of the Netherlands. And they scaled this up into a, full-scale commercial system here. First couple of installations were in 05 and 06 at industrial sites, edible oils and food processing. And then in 09, they started up their first municipal plant in South Africa. And shortly after that, a number of plants in the Netherlands, and it has since expanded globally. It took a little bit longer, however, for them to make their way into North America. Just how we work projects is a little bit differently than what's done overseas, apparently. So they partnered with the manufacturer, and Aqua Aerobic Systems has a pretty long history with biological treatment with the SBRs. And obviously have a just decent standing in the wastewater community in the US and Canada. So we've been working with this for a number of years. And notably, did some piloting, started up a demonstration reactor in Rockford, Illinois, which is where we're based out of. So this is at the Rockford treatment plant. It's a 40 MGD facility. So a little bit bigger than what you guys have in Lewes. So that's been running for about 5-6 years now, and it's operated by our R&D department. We use that for R&D purposes, customer visits, operators to come out and get accustomed to kind of the equipment and control structure before they start up a plant. So it's been very beneficial for Aqua. And actually what they're doing now is they began construction a few weeks ago on a 10 MGD Nereda expansion at their site. So they'll have their 40 MGD flow through, just aeration basins, and then we will have that Nereda off to the side to take on some additional flow. Back in January of 2020, we started up the first commercial installation in the United States down in southern Alabama. This is the Redneck Riviera down here. They're only about 20 miles from the Gulf Shore. And that's been run by, they call it the Redneck Riviera. It's not derogatory.
That's not you. That's Justin, yeah.
So they Lee down there, the superintendent, he's actually had his eye on this technology for a few years. We were not licensed yet, and he had went to the Dutch and asked, "Can I get this?" They said, "Well, no, we don't have a means of selling it to you right now." So he was chomping at the bit to get his plants moving in this direction. So we'll hit on that a little bit. 2021, there were 4 startups. One of those was just a 1-year-long demonstration and for direct potable reuse in Oklahoma. They just presented a paper at Left Tech this year. Wolcott, Kansas was started up January of last year. And then this year, we are currently in the middle of startup 3 of 4. So it's been a big year for us. And we'll see that number probably be around 3 to 4 startups for the next couple of years, and really seeing the technology grow. So internationally, there are 70 plants running, maybe 71, depending on how my emails look at the end of the day. About another 30, 35 under contracts. That means they're under design or they're under construction. Again, global technology, it's been around for quite some time now, 20 countries, not quite on all the continents yet. I can give you guys the one that we're not going to be building on anytime soon. With that being said, though, there's a couple in Australia, Hong Kong, Jeddah, Saudi Arabia is going to be quite large, so it has become fairly expansive. And of course, the US and Canada will open a whole another door here. Yes.
So since 2020, how much has changed in the technology or the application?
That's a good question. Application, not drastically different for the technology itself. I will hit on, I did mention that we do our own R&D work, even though we aren't the actual owners of the technology. We're really in a partnership with Royal Haskoning. Now they are 10,000 plus person company and probably have the same number of people dedicated to the Nereda technology as we have as a company, but we still do extensive R&D. So that demonstration reactor, one thing that was really important in the US was the ability to retrofit aeration basins or clarifiers. And with the batching process, you're generally looking at about a 20-foot depth to ideally maximize your depth there and for the batch volume. But what we did is we ensured that we built that demonstration reactor with the ability to move the decant weir so that we could test it at different discharge depths. So now we will design down to 14-foot depths. leachate. They don't do leachate over in Europe. They don't do the landfills. So leachate is something that we'll see here that we will apply it to. We don't have one built with leachate yet, but we have a lot of we have extensive experience with our SBRs with leachate, so we can apply that knowledge to the Nereda system as well. So nothing too drastic, but just some tweaks that maybe make it a little more friendly to the United States. And we continue to push and see where it can go. And in terms,
future things you're looking at?
I would say nothing that I can share right now, but yes, we do aggressively look at how can you not just incremental tweaks with this, but I mean, how can you take this even a step further? As we'll see, it's very much a space saver, energy efficient. What can we do to make it even better is, you know, the question that comes out, you know, but nothing in particular at the moment.
If the first one was in Nereda.
Yeah.
What are you doing now that's different?
There would be, one thing would be essentially for our aeration system and diffusing air out of that. As you turn it on, you need to blow off some air. We had previously used a bubbling tube that actually ran towards into the reactor, and that just let too much air out. And what we do for an SBR, it wasn't an issue because of how the SBR acts, but with the Nereda, we fill it and decant at the same time. So that was just causing a little too much agitation for what we wanted to see during it should be a pretty stagnant phase. So now we use an external muffler off that pipeline, and we just muffle or exhaust to the air now. So that would be a small change. Doesn't save anyone really much money, but it's just a small design change that makes it just a little bit better than it was before. So that would be an example. A lot of it would probably come from the programming side of things and ensuring that you have any, I'm not a programmer by any means here, but really making sure you have any safety precautions necessary to prevent flooding your headworks, you know, ensuring that your valves are going to open and close when they're supposed to. If you lose power, how will the system respond? So there has certainly been, I'd say, additional development on the programming side is where a lot of it has come from. And that stuff doesn't take anywhere near as long as vetting out a new process there. Another big thing would be changing from a standard of an ammonia analyzer to an ammonia probe to reduce your maintenance and your costs in that. Not every plant needs ammonia measurement, but for plants that are looking to achieve a lower level of ammonia, it allows for really fine-tuned control. For example, my plant in Kansas needs to hit 0.6 for a couple months every summer. So we want to ensure we are hitting that without over aerating the system as well. And when you add in that probe, it's going to make everything more efficient. Now the switch from the analyzer to the probe doesn't require the same level of maintenance as the analyzer. And we actually, that Foley plant down in the Riviera, they just switched out, and I shouldn't say just last year, switched over from having analyzers on each of their 3 reactors to the ammonia probes. And the return on investment should be about 2 years to recoup the savings that you get with using an analyzer. So we've made it, there's a lot, and there's plenty of other things. I should move on to the next slide, but yeah, plenty of other things we can talk about, but we continually try to improve it. We're not doing anything so far that's been so drastically different that if you go to one plant, it's going to look the same as the other plant. You won't see anything visually that's significantly changed. Any other questions on that topic?
So when somebody gets a new retrofit down that curve, how does that get costed out?
The costs?
Yeah.
Well, that's a whole nother question probably from this. So the cost is going to be very dependent on your design, what your flows are, what your loads are, and then that's going to dictate your volume requirement. And that volume requirement is going to further dictate your cost. The piping, what sizing that needs to be, obviously your flow and your cycle time will dictate your blower necessities. So, okay.
My point is that we're basically on a learning, you guys are on a learning curve.
Oh.
Innovation curve.
Okay. Yeah.
Innovation. So there's things that you're going to have a year from now that you don't have necessarily now.
Mm-hmm.
How do you help us help ourselves by having these different kinds of nuances?
The programming changes we can make remotely. We can do anything that we're upgrading or that we think will be beneficial, we can do remotely. For anything controls wise, that's something we're going to take care of. One basic example would be If you do lose power to your system and your main control goes down, you can run this off just a basic PLC system, off what we call an interim recipe. So it's going to keep at least your basic phases going, your basic cycles running. So that's something that now we are going to take it a step further, and we're going to adjust that interim. If for some reason that needs to run for an extended period of time, it's going to now respond to changes in flow. So if you get a high flow coming in, it will shorten your cycles to allow more flow to get through. So something like that isn't a big. We're in terms of anything large and mechanical, there's nothing in the works that we have that we would be coming back to any sites with. That bubbling tube was something that took, half a day for one of our techs to go out and adjust. And I think that was maybe the last plant that had the old standard in, and now this external muffler is the new standard. So nothing is happening right now and if it were, we would make sure that we're designing towards that standard in the future. And if we do change anything before we get too far, it'll be, reviewed with you guys and the engineer to determine if that's a change that we would want to make. Something like the ammonia analyzer or ammonia probe would be probably a good example of that one. It's not a big mechanical system, but it is still something that's being designed for in terms of your, electrical components as well. All right. So jumping back into this, so looking at we'll like the applications. I'm not going to each of them here, but more to show the range of flow. And there are a variety of applications in there. So on the low end, which I don't think anyone can really read the numbers here. So smaller plants, you've got 50 to about 100,000 gallons per day. Those tend to be industrial applications. Actually, the one is Kahului Airport on the island of Maui. That was started up back in March and April of this year. It's safe from the fires, as are my operators, but that's been chugging along now. And on the larger end here, the biggest plant currently running is outside of Dublin, Ireland. It's 165 million gallons per day. If you guys need to go see a plant, I know it's really, really just in line with what you guys are at. Definitely go try to get a trip out there and bring me with. I haven't been out to that one yet. It's pretty impressive for the wastewater people, nerds in here. They have 24 SBR reactors that are stacked one on top of the other. So you have 12 huge reactors, and they're about 12,000 cubic meters. I don't know in the US units right now. So the sites get pretty large, but it's very modular. So if you start off with maybe a few reactors, you can add on a couple in the future, depending on what your flow needs may be. All right. Now in the United States, where we're at right now, we've got 8 plants running. I think this is a little outdated here, but a demonstration reactor here in Rockford, Illinois. We're about an hour and a half west of Chicago. Very much a Midwestern town. You've got a lot of corn, a lot of soy in the area, and then obviously some manufacturing from companies like Aqua. And they are building a 10 MGD facility, as I mentioned. First one, commercial. Here we've got that Foley, Alabama, down in southern part of the states there. So obviously we do see a lot of hurricane and tropical storm activity. One of the drivers there was to get a dense sludge that wouldn't lift up. They would lose sludge from their oxidation ditches when they'd get really high flows. They also had concerns about salinity as well. They're not right on the shore, but they had a lot of I&I issues. Let's see, I'm a little bit behind on updating this, but we have South Sioux City in Nebraska started up earlier this spring, or summer, I should say. That's actually a slaughterhouse application. It's about 95% industrial. I think it's actually mostly all industrial at the moment, other than maybe a few other little areas getting in there. And we've got this one in Bainbridge, Georgia. I think we were seeding that last week, and I'll be checking in with my field engineer later today. He'll be getting back to site, so that'll be up and started soon. Greenville, Michigan, that'll be started up next month, and you can see there's a couple other plants there. Idaho Springs, Colorado, that's up in the Rocky Mountains. It's truly a highway town. You drive about an hour west of Denver, and there's a little bit of a town on either side of the road, and that's about it. So they had no room to expand at that site. Whitefish, Montana, it's outside of Glacier National Park. And then obviously the Maui, the Kahului Airport I mentioned there. So all the other dots you see on there, purple means we're in construction or the submittal phase. The red is we've piloted at, and then the blue dots are projects that we've been pre-selected for. So they're likely going with Nereda.
Oh, what's happening in the DC area?
We don't have a lot of activity out here, but are you thinking of this one we piloted at? That was Fairfax, Virginia. And that was piloted some years ago. I'm not sure where we are right now on that project. I think I have heard it kind of maybe coming back and moving forward.
Still part of their long-term plan.
Yeah, that was not that. And like Cedar Rapid, Iowa, those were far out projects, larger ones. So this is kind of, you guys are in the last little holdout of, as you can see on the map here, and actually Ontario, I've got a few projects in Ontario now. So we're not looking to do much in Quebec because they're very French and they like just working with other French people. So we're kind of going to let that one be. But yeah, you guys kind of the New England, the Northeast, you guys are kind of the last holdout in terms of getting something newer here. You can see that Saco, Maine, though, they're going to be bidding, I think, later this year, early next year. And finally moving forward on that one. So kind of getting the inroads here with you guys. And my aunt actually lives in Philadelphia, so I always get articles on wastewater in the area from her. So and then just for little bragging rights here, it was ranked the #1 technology of the 2010s. The 2000s was an MBR, and then really the one I call out is the Wolf Creek. Here was the plant of the year globally, runner up to Sydney, Australia, and I think they beat out Jeddah Airport, and then there was another large plant they beat out. So there's a little, again, 3.5 MGD plant that was a runner up for a global recognition, which was pretty impressive for them. We've got a hardworking team there that definitely deserves it. All right, so I'm going to move into more technical stuff now. Are we ready for that? You guys can answer the phone if you need to. I don't mind.
I thought I turned it off.
Okay, so we can just let it go.
I was hoping no one would hear it.
So what exactly does Aqua Nereda offer? We're here for a reason, obviously. I feel strongly, I'm not a salesperson, I'm an engineer, but I still feel strongly about what this technology can provide, and I get to see it out in the field fairly often. So we're looking at this, and we'll get into the details here, but it's a small footprint, which I know is a driver here after being out on your site. That's going to reduce your cost savings. And biological nutrient removal, that's going to be a big one. It sounds like you guys have definitely total nitrogen and possibly phosphorus in the future. I'm surprised you don't kind of have that yet with where you're located, but could definitely come your way. Big one here is going to be the energy savings, especially over the MBR system that y'all are running here. Really trying to reduce that, and obviously with low cost installed cost, low O&M long term, you're looking at the lowest LCC on this. Operational simplicity, there really is a transition here from more of your hands-on mechanical equipment to keeping up on those instruments, just keeping those clean and reviewing process trends and ensuring things are running as they should. You can access the controller system remotely, even for the operators. If you need to check in when there is a storm coming in, you shouldn't have to run into the plant for that. It'll hook right into your SCADA. And finally, the modular expansion, which I kind of hit on. So a lot, yeah.
On that last chart that you had.
Yes.
And is there the ability to look at each of those and say, here's our plant today that we have, and here's what yours will be different by how much when it comes to electricity, how much when it comes to nutrients, how much.
Oh, and like what the savings would be long term and what you could expect to get. Yeah, we can certainly. I have data from sites out that have been running and have shown remarkable energy reduction. Wolf Creek showed about 50% savings the first year that they were running their Nereda versus the oxidation ditches that they had, and they were still using a lot for storm flow. So we've seen the data come back that shows the energy savings like that. I mean, you guys are welcome to call the operators at Wolf Creek, running for almost 4 years now is a good one to reach out to. And, they know their system really well at this point in the technology. I can't say anything, in particular, how things can change over time. So I don't know that the plant in Idaho Springs, the 2-basin SBR retrofit, it was drastically over-engineered. It was designed for 1 MGD, and they never see more than 0.5. So we are running just on 1 reactor now. There's no need for him to run the second one. Why keep everything working so hard? So he still has sludge sitting in that reactor. I don't know what he's going to do with it long term. He could eventually process it and waste it, or add it into the other reactor. But right now he just bleeds some air into it to keep it from going septic. And so I can't say for certain what could happen, but I can tell you what we can design it to achieve.
And if I could just add.
Yeah.
Something to that question, there is that as part of every evaluation, life cycle costs are
Mhm.
really key. So, I mean, that's figured on every project. From a capital standpoint to that long-term operating costs. So that's something we can provide, and we provide it all.
Oh, yeah. And that's something we can certainly work with, when you get a consultant on, they're going to do a full-fledged of everything, but we'll give you everything you need for the system and what you can expect it to do. Now, if you guys end up having your flows are twice what we designed for, I can't promise we're going to do what we need to with that case. So, again,
Wouldn't be here.
everyone's gonna have a few issues there. So again, I can't tell you exactly, but I can tell you what we can design to meet, and I can say that the plants that we've been running so far have met those obligations at the flows they're at. No one's at their obviously design flows usually don't come until a few years down the road, but there's a lot of flexibility with this as well. Yeah, so we can be certainly well under. And then, your nutrient limits, it's all stuff that comes down to the engineering, ensuring you have carbon to facilitate your nitrogen and phosphorus removal. So that's all stuff we'll talk about with the engineer during the design phase. But again, we want to make sure our data is good, that we're basing everything on. All right. So where the benefits come from. So we're able to get this because it's similar to a batching process like an SPR. We're using adjustable cycle structure. So when you talk about operators and what training they may need, anyone with any sort of a wastewater background should be able to jump into this, and with some additional training, obviously learning the new technology, they'll be able to run it. Someone with SBR or activated sludge experience in general is, really beneficial to have into this, because they're going to be able to recognize when something may be off. If you see too much scum or too much foam on that reactor, they'll know when to identify that it doesn't look right probably. And then the same causes of an activated sludge upset are the same that we would see with a Nereda, because it's the same biology. So generally you're looking at a same cause. We should see should not be affected as much by any sort of unpleasant conditions coming into your site. So anyway, so it's still quite similar. You see much more rapid settling. And then obviously you have the enhanced nutrient removal, again, the batching process. Now what we'll see with this granular sludge, Tom, do you actually mind grabbing my purple bag there? I have granules in there I forgot to take out. I want to pass those along.
While he's doing that, I keep reading that all the treatment is in a single reactor, but you recommend.
So yes, I know that's wrote everything. I know that is confusing. So that's not you would have a huge reactor for some plants. If it's 40 MGD plant, you are not going to build a reactor that big. So this is where it's called a batching technology. With wastewater, a lot of plants, such as a 5-stage Barden-Foe system, the water is always flowing through the reactors. It starts at point A where it comes in, and it just keeps going. It runs through all those trains. You'll have, say, an aerobic treatment up front, then you have your aerobic, you have the anoxic, aerobic, anoxic. So it goes through different tanks to get different treatment environments. Step change before going to Nereda was the development of a sequencing batch reactor. So it was taking wastewater treatment, that same flow stream that you'd have, but having all those environments within one reactor. So you're still getting anaerobic treatment, and anaerobic treatment is for phosphorus removal. We have no oxygen or nitrates available. So the bugs are going to eat up you're targeting a different biology, a different type of bugs to work. You have anoxic treatment and you have aerobic treatment. All three of those environments can occur within that single reactor. So Aqua Nereda is often referred to as an SBR with AGS, with aerobic granular sludge. It is quite similar, but we operate a little bit differently. Our cycle structure is different, but it is still a big deal. It's all in one reactor. So I get where that misconception can come from, but you're not going to be able to design a reactor big enough for a plant that's 100 MGD. So that's where it comes down, is that you're getting those distinct treatment environments just in one basin there. Does that make some sense? Or I can even draw a picture. We were talking about Bill. He's apparently an expert draftsman on the fly here. But essentially you have water flowing through different areas. So these are all going to be
Yeah, but you have a slide, I think, with that, don't you?
Oh, no, I don't have this one anymore.
With the flag state?
No.
Yeah.
No.
I'm just thinking, we're in the 1.75 million gallons per day kind
So
of.
this would be a traditional one. No, we'll still do a few
Design
different
flow.
tanks for you guys though. So it's kind of a probably in the wastewater industry, when you're used to hearing it all day, it makes sense. So this would be traditionally, you'd have 1, 2, 3, 4, 5 tanks. The water's just going to keep going through it the entire time, but there's different targeted treatment zones. In this case, we're getting all that water into one reactor, and we're going to change the conditions within that reactor for different targeted treatment, and then the water comes out. So it's a batching process where in this case, it just flows through. So the batching is not new. It's been done for 50, 70 years now, with plus for those sequencing batch reactors. This is taking it just a little bit innovative step. And what we're doing is we're forcing it to turn the sludge, which you have in any sort of technology, into the granular shape. And the granules settle very, very quickly and allow us to operate at a much higher mixed liquor relative to conventional activated sludge, which is very, slimy and viscous and has no organization to it. Feel free to pass them around. So you can see they settle very quickly. They're sitting in formaldehyde in there, so it's the biology is all dead. Obviously, there aren't any bugs in there. I don't go home and feed it dog food and aerate it or anything every night. So the biology is dead, but that granular structure is still there. So what we get from that is that, again, so I know that the batch kind of is a little bit weird there, but it's a, not so much flow based, but it's your treatment targets, your treatment environments that we say that the batch, the single reactor, that's why it is beneficial. You really see batching being really good for industrial sites, especially, or for big diurnal flows, because you can target you may have to extend a cycle so it can adapt to the changing conditions a little bit better than a flow through plant.
Paul, also, it's not a single tank though.
No. Yeah, it's those tanks get added on as you need more flow. So that's how that works. So
or a town. Say, million and a half gallons a day in the summer, and million and a half gallons a day in Christmas time. Well, 600,000 the rest of the time.
I'll probably, no, we're not going to run, we don't want to take reactors down. That's going to be too much work for operators. You can, but you'd have to be taking a reactor down when you go into summer or go into winter and bringing it back online during the summer. That's too much work. For some extreme sites, there is a ski resort we're working on in Colorado where that may be the case, but that means they have almost no population during the summer and then explode. It's not, you guys are pretty standard. What you would do operationally is just run at a longer cycle time. You don't need to push as much water through, so you're just going to give it a little more time in the treatment, and that's all stuff we're designing around. When you design a plant, you're not assuming it's going to always be what those design numbers are. You're going to start off maybe 10, 15% of that design flow for some greenfield sites and maybe a newer area, new construction. So you just are going to adapt to that. So when we're designing it, we're certainly aware of the fact that you have, variability in what's coming into the plant.
Yeah, I have another question. So if you have a couple of tanks, does the flow go from one into the other?
No. Okay, no. So that's another good question. And did you have that layout there, sir? I saw you had, so that one has an influent buffer to it. So what you'll do is water. So what you could, if you have, let's say 3 reactors, what's going to happen is one reactor will be filling and drawing, because we fill and draw at the same time, fill and decant. Let's say it's a 6-hour cycle. The reactor 1 will fill draw for 2 hours. Then it will move on to its react phase. As it's doing that, then reactor 2, that's going to start filling and drawing for 3 hours. And then reactor 3 will fill and draw for 2 hours, whatever my structure was. So they're just going to alternate. Now it looks like Thea had put together a 2-reactor system for you guys, which is fine. You're a little bit smaller flow. So what'll happen is that she also has an influent buffer there, and that'll just store flow during periods that you're not filling the reactors. Because the cycles get so quick, you won't have that back-to-back fill draw because it's a little bit shorter with just 2 reactors. So the water will sit in the influent buffer. You guys have that EQ now on site. So it would function kind of similarly to that, but we'll pull water from that to one reactor when it's ready, and then we'll pull it into the second reactor when that's ready. And if we want to work under a fill draw decant, such that one's always filling and drawing, we can certainly put together a design for that approach. You guys can compare the two. You're at a flow point where you could kind of go either direction. Wolcott and Whitefish plants, they're a 2 MGD average design flow, and they use 3 reactors, no equalization or buffering up front. They just fill draw one after the other. So you guys are at the point where you could do either. And that might be something with your operations firm. They may have input on what they would prefer as well to run.
Are you saying that with the 2 reactor system, you have to have?
Yes, that would be different than an SBR.
Yep.
Because SBRs, they have a longer cycle time. With these, you're shortening that cycle time so much that you can't, when you're down to those 2 reactors, that fill draw becomes pretty rapid. So it gives you a little more flexibility. Once you get to that 3 reactor system, you're going to have it's going to be elongated a little bit. So you can, if you have a 3 reactor system, and you're eventually going to have to take a reactor down for maintenance, replace the diffusers, so you can run on those 2 reactors for, a month or 2, whatever long it takes. Probably not during, peak conditions. But, long term, you can do it 2 with the buffer or 3, no buffer. So again, you guys, it looks like your design flow is kind of at a sweet spot where we could look at either different option. So
Major difference would be footprint. By adding the 3rd reactor, that's going to be bigger than your buffer tank.
Yeah, and it'd probably be a little more expensive because there's no equipment in that buffer, obviously, other than pump. But then you look at the pumping costs. So again, you can run both options here and see what will be more beneficial for you guys.
So that influent buffer, you maintain mixing in it for aeration.
Yeah, you can use a mixer. There's different options for that. Usually the engineer will decide exactly what they want to do up front, different areas. We can provide the equipment for the influent buffer, but we're flexible on that. It could be even just how long it's stored for. Some places, if it's small and covered, they may not even worry about it. You'd want to use a mixer in this. I do in Idaho Springs, we do have it aerated. As we get into this, we'll see I do not want oxygen when I'm filling this system. I want it because I'm trying to deplete the oxygen pretty quickly. So aerated up front isn't ideal, but Ed does it out in Idaho Springs, but he just uses a little bit of air to pulse. But his buffer is covered and he's in a little treatment area away from a residential community. So he doesn't have any odor concerns. His plant doesn't smell, but with that influent buffer being not treated yet, that's where your odor is going to come is prior to, your biological treatment.
So
I think there was sensitivity to the microbe, to the microbes, so I have a lot of filaments. How does it react?
So the technology deselects for the filamentous material through the selective
What they all
wasting.
say.
Well, that's what we do though. That's how we waste out of the system though. And I've managed now, it's plant number 7. It's not something that I've seen extensively in the last 4 years. I can't say it won't come up. But usually the issues where we have any extensive growth is during startup, where you're going to see kind of scum and foam develop. I did have Whitefish, Montana. Actually, their loads have definitely, if that plant were to be designed now, I would actually recommend a buffer up front because of extreme diurnal variation. And they not only have extreme diurnal variation, but it's very seasonal as well because they're right by Glacier National Park. And then they're also right by the Whitefish Ski Resort. So when ski season comes into play, as soon as you're after Christmas, their influent carbon almost doubles. And these guys came from running a lagoon, so weren't as cognizant of your sludge yield. So they did have a bit of a buildup of sludge. They weren't wasting adequately, and the system wasn't designed to really handle like 750 milligrams per liter carbon when it was designed for like 250. So their wasting needed to increase. And at that point, they had too much, I won't say filamentous, more flocculent growth. We saw their granule concentration decrease. So they kind of spent a week just wasting out a little more aggressively, and they were back to normal. So from my experience is that it really does deselect for the filaments, because that is how we granulate, and it's every single cycle. That's just how we waste out of the system. If you're not wasting, then that's not good, because that's how the system needs to operate. So
if you have the counter steer and chlorinated, how would that affect the granulation process?
and sorry, what was the question?
When you have the counter steer, essentially you start to chlorinate the RAS. How would the granulation react to that?
I don't know if anyone currently chlorinates their, well, we don't have returns with this. I was thinking, sorry, RAS. We don't have any return streams with return activated sludge streams.
So if you don't have any RAS, you wouldn't be able to fight the filament.
And that's what I'm saying, is that we're deselecting for them. I don't have to fight the filaments.
It's all in a single tank.
Yes,
I
yeah.
know, but if it happens.
But what I'm saying is that it doesn't, because that's what I'm wasting out of the system.
You may wanna run through-
Yeah, I think a lot of the questions will get answered as we go through this. So, because we've got to figure out where the granules even come from. You guys don't even know where these things come from. For all I can, I mean, you can buy them on Amazon as of right now, for all you know. So, just not what we're doing. So, this is pretty true. This is one thing they don't have yet. So let's hit into that now, because we'll start, I think, answering some more questions. But this is developed just through the system itself. This is self-sustaining, and this is how we get them, is by wasting out the filaments, any sort of flock material we don't want in there. And that is up to operators to gauge and keep an eye on. So it's not, it's not like it does this on its own. It still needs someone to, to watch it and keep an eye on things. So just taking a step back, what exactly is this in here? We talk all about Nereda, which is the technology name, but this is aerobic granular sludge. This is something that other plants can grow if they have the correct selection mechanisms, but no one else does at the moment. So we get these developed, again, no media carrier. We're not adding in any chemical for this. It's just fully a sustainable process through selection mechanisms in a cycle, which we'll see. We need them to be at least a minimum diameter of 200 microns to get a dissolved oxygen gradient to develop, where you have aerobic conditions on the outside and anoxic in the center. So this is how we're eliminating the multiple tanks for the treatment. Again, in terms of getting your different treatment environments. But you have all biology in there, which makes it more robust and resilient. So not to derail, but a couple of examples. One would be, again, Idaho Springs. I got a call from Ed back in, I think, early March on a Monday night around 6:30. And Ed knows what he's doing. We have a 1-800 customers, 24/7 customer service line. And, this was the end of the day. It was weird to be getting a call from him. And he said, well, I have pink effluent. And he sent a picture. And he had red sludge with that. And I just, well, that's not something that, the system is going to be making color unless, you're dropping food dye in. Well, they weren't dropping food dye in, but a local car wash had done maintenance the following Thursday on I don't know why we add dye to our car wash soap, but we do. And they leaked 20 gallons of dye into the collection system over the weekend, which for a plant that sees 300,000 gallons per day ends up having a big impact. And with that dye is hydrophobic, it's non-biodegradable, it's toxic. And you could see the impact on the system. They tested him. I mean, the operator left Friday and came back Monday morning to green, to pink reactors. It was not what he expected for the start of the week. They ran tests on COD, got their ammonia, and their TN and nitrogen, effluent nitrogen doubled compared to what it usually was for them. It was, like 2 instead of 1, and their effluent COD had just about doubled. So they found the cause of this, and they fixed it. And within a day or two, we did see those numbers come back down. I do have another presentation if we want to see that with the trends, but it recovers very quickly because of all the biology that we have in there and how it's layered, which I have a slide on here. Other big one is that it settles very fast, which you guys have seen. We can quantify that. We're about an SVI 5 for AGS is comparable to about a 30-minute settle time for your conventional sludge. So it just settles much more quickly. And obviously that saves you time in your treatment cycle. A sequencing batch reactor, we designed to have a minimum settle time of 45 minutes. This will settle in 15 minutes once you're at your full granulation after a few months after startup. Oh, and then the mixed liquor. Yeah. Oh, yeah. Do not add polymer. Don't add polymer on my startup. Not while I'm granulating. A mixed liquor, we're designing at 8,000 milligrams per liter in most cases. Every now and then it may go up or down 1,000 milligrams per liter depending on the design. You guys are standard. Now that doesn't mean plants run at that. If you don't have the load to support it, you don't need that biomass there. So most of the plants we have out there right now are somewhere between 3,000 and 7,000. Wolf Creek, the Alabama plant, did get up to like 10 last year, and they just don't need that much biomass. It forced their something called a food to mass ratio down way too low. Yeah, there wasn't a good ratio of your incoming mass of food versus the biomass that you have in there. So that's something for our operators. That's something that they'll use to kind of guide their operation or how frequently they should be wasting. Because we eventually will waste granules. They'll get so big. And I think you have questions on solids handling. We'll get to that later. So we do eventually over time, but mostly it's just going to be that flock material. Inherent biological nutrient removal. So this, Barbara, is where we're kind of getting with that all-in-one reactor. You have discrete aerobic and anoxic anaerobic layers. Now it's not just in each reactor, but now we're talking in each granule. You get these different treatment zones. So it's taking that batching process even a step further, and now you have all those environments within just one little granule. So we can nitrify and denitrify at the same time, and then the BioP down to 1 milligram per liter. And we'll kind of see why we can achieve that good BioP without chemical. And then the nitrification, that TN limit's pretty standard for secondary treatment processes. This is our demonstration reactor in Rockford, Illinois. This is the Four Rivers Sanitation Authority. It's a 40 MGD facility. You can see the primary clarifiers in the back. And they're actually replacing a bank of those with our filters, our primary filters. And so again, 200,000 gallon per day reactor here that Daryl is the main operator of. And you can see he pulled the granules out. And this is something operators will do as one of their tests. He's dumping that through about probably a 2 millimeter soil sieve. And these are what they look like out of, a nice mature system that's been running for a while. So it looks kind of fun. A lot of people call it wastewater caviar. Compared to sludge you pull out of a conventional plant, it's, as you know, it's just going to run through a sieve for the most part. But this gets held on. Now you have varying sizes. They start off as tiny little black dots. After you seed a plant within a couple of weeks and you pull your sludge, you'll start run it through a set of soil sieves. You'll start seeing just tiny little black specks, and that's what they start off as. But as you pick them up, we can pump them. We pull them out of our Nereda here demo reactor for pilots. We seed it with that. So they have some sturdiness to them. They aren't just going to, breeze comes by, they aren't going to fall apart. They take a bit of pressure to pop. And Tom's heard this a million times already, but I do I think they're similar to mints that were around about 20 years ago. You'd bite into them and you'd bite through the membrane. There'd be a burst of, liquid minty freshness. So I haven't eaten them, but they are very similar.
Take your word for it.
Well, you could bring these home to the wife one night and say, I got this caviar for the evening. What do you think? But there is, but they are sturdy. They don't it's not just a little bit of a press. You gotta, pop them a little bit. So, they get pumped okay, and they're not just going to disintegrate, but they're also not going to affect the solids handling negatively, but we'll get to that again later. So here's your spectrum of activated sludge. So on your left-hand side is flocculent sludge. So that's kind of what gets left behind if you were to drop it through or dry it out. That's kind of what you'd see left behind in terms of any sort of solids there. And then you can densify, and a lot of well-run flow-through plants or ones that have good selection zones have the anaerobic selection, those different tanks. they'll get some level of densification, and some technologies out there do give you densification for incremental, maybe improvement in your system. Maybe you are having issues with the filaments there and they're doing some selective wasting to get this to occur, or they're adding that anaerobic phase up front. But no one can quite get to the true granules that you see here. And once you're at that point, that's when you can run at that very high mix liquor without inhibiting your aeration system. That's when you have that 15-20 minute settle. That's when you get the simultaneous denitrification, because those granules get so big, you get those nice big anoxic pockets. Really around 600 microns is when you see the denite really pick up. So compared to that flocculant sludge again here, so this is, a drawing, but it's a mixed microbial community. You can see that we have the same bugs. We have yellow bugs, pink bugs, purple and green bugs on both sides here, but it's how they're organized. So on this side, you can see that how we're operating this plant is the reactor, the cycle structures, we're forcing that biology into that layered community. And that's because you have aerobic conditions on the outside, and that oxygen can't get in deep enough, so it becomes anoxic as you get deeper. When you get like the 5 millimeter granules, that can get even anaerobic in the center, and that's when you start seeing it kind of fall apart, and it becomes a tiny granule or many tiny granules. So that's self-replenishing. So even if they get big and they kind of fall apart, it's going to stay in the system, or it'll become a little speck and it'll get wasted out with the lighter flock material. So when you look at a solids retention time in this for the SRT, it's variable. Whereas when you're designing like a SBR, a flow through plant, you're looking at a consistent SRT. In this case, that flock coming in is going to be a couple days old, and then those big granules could be a couple months old, but it's totally fine for the system. I'm just not using an SRT to guide my operation.
So what do you use? Just
Food to mass ratio. Yeah. Yep. So like that Montana plant, they kind of know now in January, February. And I think, again, these operators they just came from a lagoon. They aren't as process driven. They weren't tracking data. And I think just after COVID, that part of the country's had a pretty big population increase, and just northwestern Montana in general. I can't afford the low income housing that's right next to the plant, is how expensive it is out there. So a lot of people, with money from California flocked out there. They're building their low income housing starts at $400,000 right next to the drying beds. So I don't know. Although being out here, I think housing is way more expensive out here than Rockford, Illinois. Go figure, people aren't flocking to the cornfields. So with the granules here, kind of going back to that robustness I was talking about and why we have that more rapid recovery when you do get upsets. I don't love getting a call like that, but it's good to see how it rebounds. But they're not perfectly spherical. And I know it's tough to tell here on the monitors, but if we look over here, see how there's blue on the outside here and blue on the inside? Jeff, I'll go to this one next. Here, blue on the outside, blue on the inside. I'll send you guys a PDF of this. Essentially what it's trying to show, this is a fish fluorescent analysis. And what you can see is that blue represents nitrifiers. So you can see them on the outer edge, but because this isn't solid, it allows your substrate, your influent carbon, that food, to penetrate into the granule, and you still have populations of biology in there. So if you have a toxic shock to the system, like Idaho Springs had, is you can kill off that biology on the outer edge, but it will recover more quickly because you still have that kind of backup biology, if you will, within the granule. So that'll start replicating and you can recover more quickly. I know another good one, I'm trying to think of, fortunately, we haven't had too many hiccups here in the US, our plants yet. So another good one is APA Netherlands, that has been running for 12 years now. They piloted alongside their existing flow through conventional plant. It's predominantly slaughterhouse waste there, but they somehow got an upset where the pH coming in skyrocketed, killed off all of the biology in their conventional system, which took a good 2 or 3 months to recover. And the Nereda was back to normal in a week. It saw better performance in a few cycles and then back to the effluent requirement or effluent that it needed pretty shortly thereafter. So I try to keep track of our upsets here, but fortunately not too many yet. We've had a fog dump into one reactor. It still performed pretty well. It didn't look good for a couple of weeks, but we still got the nitrification that we needed out of it. try to think of any others if they pop up while we've been going through this. So this is just to quantify the biology that you have in there. So we're looking at PAOs, which are slow growing organisms. That stands for a polyphosphate accumulating organism. So phosphate, these are the bugs that are responsible for your phosphorus removal. And what happens is phosphorus removal occurs in two phases. The first phase is actually where the biology is going to cleave off a lot of phosphate. We're actually going to see the phosphate in your reactor increase. But when you get aeration going into the system again, all of that gets taken back up by the bugs, and it'll take up even more than was expended. So that's called luxury uptake, and that's how phosphorus removal works. Well, within this Nereda, you can see that in the AGS sample here, compared to the conventional sample, we have about 4 times of those slow growing organisms, which means we're going to be pushing for more and more phosphorus removal. So that's when you see, compared to an SBR, we're not going to guarantee 1 milligram per liter BioP out of our SBR, but we will guarantee it out of this because of that bigger increase or bigger concentration that we have of these types of bugs.
The info process has a very high bounce rate because of that slow selection.
And that's
How do
something
you-
that
how do you get that rapid selection?
you'll see.
Alright.
We'll get to it. Don't worry. We will get there. But yeah, we're avoiding that RAS completely. This is just a little marketing video. If you guys ever make your way out to Aqua, you get to see this in person. But these are sludges pulled from our demonstration reactor on the right, and then our the Rockford's plant's flow through system. So they take on the same influent. Rockford does have primary treatment, and we just take on raw influent to our demonstration reactor. But essentially, you can see that the AGS settles pretty quickly. This was cleaned and run through a sieve. So there is going to be some component of that flocculant material at all times because you always have fresh influent coming in and you're always in that granulation process. But essentially, it settles significantly faster. And that's just some off-gassing off the other one there. Okay, where do granules come from? So this is where we're getting into it. We'll start seeing how these all come about. So when we seed, we start with conventional activated sludge, generally with a new plant. In the Netherlands, they'll throw in some AGS because their plants are like an hour from one another. No one in the US is paying to ship, some gallons of sludge across the country, unless you're doing a pilot maybe. So takes maybe about a month longer to hit your full granulation, but when you start up, but we still are operating or will operate to ensure that we're meeting your effluent targets at startup though. So that is a couple slides on that, but I just wanted to get that out there so that we don't, have any concern about the time we say it takes time to granulate. So I think I hit on these, no biology, all biology, no media carrier. This is developed just through normal everyday operation, just within your reactors. You're not buying them from Amazon or from Aqua. So there is attrition. You do lose them purposefully, but it's not like a plastic media that you would add in there. But we just form it from the conventional sludge and it just, again, replenishes through normal everyday operation. Maria. So as those granules get bigger, obviously the settling improves. You're going to increase the biology in there, makes it a more resilient process. But where exactly do these granules come from? And there's 6 main mechanisms. So Hans, you might want to read this paper by Edward Van Dyke. I can send it to you after this. Anyone who's really interested on the wastewater side of things. There's 6 selection mechanisms that have been identified. Here's that breakage where I even mentioned how the big granules fall apart and become tinier ones. The 2 main ones we'll look at are selective feeding and selective wasting, which are really nothing new. It's just how they're applied and utilized within a single operation here. Even things like your substrate type, obviously certain substrates facilitate more growth and et cetera. But the 2, and these are the 2 that operators have control over. Unless they add certain substrates, but probably not necessary. So first one is hydraulic selection, which is essentially just a selective wasting, which is not different. A lot of plants employ it in one way or another, or they Frankenstein it in to get rid of filamentous bacteria. How we're designing this system, or how it is designed, is to ensure that we selectively waste every single cycle, but we're doing it within the reactor itself. There's no surface wasting on this. unless we have scum removal, which we can also talk about. So what we do, and we'll see an animation on this, but what we're going to do is let the heavy, dense sludge settle. And even when you have conventional activated sludge at seeding, we'll start off at a 45 to 60-minute settle time. And just within a week, you're going to start seeing that settle time. You're going to start decreasing it. And we help operators determine how you do that. But just so even when you have just conventional sludge, something will settle heavier than the rest of the sludge in there. So we just start wasting it out like that. And then the second selection mechanism, which is biological, is actually even more important. I know there's a little more wording on this slide here. So what we're doing is we're selecting for PAOs. Those remember those organisms I was talking about, those phosphorus ones? We want those because they secrete something called EPS. It's an extracellular polymeric substance, and we'll hit on that with solids handling too. But that EPS, the polymeric, that's a biopolymer. And so the biology is going to begin binding to that. So that's going to start making it bigger. And that's going to also give you that biology within the granule as well, where it's not just a solid center of some carrier. It's still a natural substance. Bless you. So that, again, just within a couple of weeks, you start seeing these specks occur, but we do this through an anaerobic fill draw. I talked about how we don't want any oxygen or nitrates in the system when we're filling it, because we don't really want to have too much aeration in that influent buffer. We'll go anaerobic pretty quickly in this because we aren't going to be aerating it at the time. But essentially what we do is we optimize that phosphorus release. And as we get into the animation, it's tough to tell here, but essentially what we're doing is we're giving a settled sludge blanket. We're giving them preferential access to all that influent carbon coming in. They're going to eat that up, and then they're going to cleave off that orthophosphate and then secrete a lot of that biopolymer with it. So again, we want that biopolymer. And we'll put it together in a slide or two here.
Wouldn't it also be nitrogen?
When you're in, because you'll be anoxic kind of at the beginning, you'll get some D-nite, but you go anaerobic fairly quickly. We did have an issue at our plant in Nebraska. They sent tons of nitrates back to us. I've been having a tough time granulating there and was seeing some sludge lifting. They weren't running their aerobic digesters correctly. They weren't aerating them properly at all, and they started sending back huge returns of nitrates. So that's where I did find an issue. But now they're running the digesters properly, and there's no issue. We're getting anaerobic pretty quickly in that phase now. They have an anaerobic lagoon up front, so they come in pretty low. So I knew there was an issue, and I'm like, well, it's not DO carryover because my DO is low. So there's something going on in your return stream. So returns are something that I try to really look out for in this process when I'm operating it or helping operators run them.
What a question about the equipment that you're using for aeration. Can you not use chlorine aerators?
No, we're going to use fixed fine bubble diffusers on the reactor floor. Yeah, and it's just to get the nice lift and mixing throughout there. And you'll see actually on top of the reactor is a series of effluent weirs. And we wouldn't even use an aerator on an SBR. That would be more for...
I have to.
Smaller.
Older one? Yeah, small. Oh, we have the combination aerator mixer decanter. For a site this size, though, no, this is going to be, I guess that would be, to me, that was kind of one of the drawbacks compared to, say, our SBR, which does have retrievable diffusers even that can be pulled up and down. Now, in terms of maintenance, you should only have to go in like once a decade to replace those disc diffusers. So that's not it. That's usually not the deciding factor in terms of these. So, and you guys, I don't know if you've had to change diffusers or take things down in the past.
For the most skates, this is going to be minimum 1 MGD plants and up in our area.
Yeah.
It isn't really cost feasible. Hans might remember we had the opportunity to be the first Aqua Nereda installation.
Can I ask you, come up to the microphone so
I
this
can hear
gets
you guys.
recorded?
Yeah.
Yeah.
Yes. Is it on?
Yes.
Okay. As I was saying, we had the opportunity a couple years ago when the Aqua Nereda technology first came out to have Delaware as our first installation, and Hans might remember that it was a artesian plant, Stonewater Creek, they were landlocked and basically had to double the flow, and they were looking at upgrading basically putting in a 450,000 gallon a day Aqua Nereda system. But thanks to you helped put in a line and turned it into a pump station. So so we're still waiting for our first installation in Delaware. But that was the driver was footprint. A lot of the plants that Mark's referring to where we've done
Yeah.
the
those are the
aqua jets are smaller plants. Yeah.
I kind of forgot we even have those. I've been in the Nereda world for so long now.
Yeah.
We don't do small plants in my mind. So that's, but no, that's perfect explanation.
Yeah,
Unless there's
thank you.
usually around that 1 MGD point is where you could do an SBR. It's going to be similar in their costs. This really comes out ahead with your O&M. Unless there are specific drivers like the Hawaii plant where you have energy use and extreme footprint constraints. So, and we look at each of the plants. I have a few plants in here and we can look at each of them and see why they did them. And did you guys watch that installations update I did, that tech talk? Okay, because I did bring that presentation in as well so that we can, for those who couldn't make it, we can zoom in on a couple of the sites so you guys can kind of get caught up. So where this fits into a plant here is that you have your screening and grit removal up front. We want to, you guys have an MBR system, so we usually want 6 millimeter perforated plate. I think, either that or what you guys have, a 2 millimeter, even though it's a band screen, should still guess what we need there. That's mostly to prevent your pumps from getting stopped up from rags. That's more of just a good practice nowadays. But in this, we do have a feed grid in there that we want to try to keep clear as well to reduce maintenance. Any effluent we get out of this can go to any sort of tertiary treatment. I know this is something that we'll see. It's a little bit different here. We do a little bit of an equalization tank for something called a water level correction. And we'll show you what that is shortly. But more importantly, I want to hit on this wasting. We're wasting out a pretty light concentration here, about 2,000 milligrams per liter. So again, pretty much all flocculant for the most part until we get to a mature plant. We occasionally do need to do a mixed discharge where we will waste some granules just to keep our mixed liquor at a good level. But what we're doing is we're sending that to the small basin here called a sludge buffer, and I'll go to this side too. The sludge buffer right here, it's just a small gravity thickener, and we just thicken that up to about the 0.8 to 1% there, which is more like what you would see out of conventional plant. That's going to be doing your typical kind of wasting. But again, because we're flocculant and so light in what we're wasting out of the system, because we're deselecting for that lighter material, we thicken it up a bit. Now we have that little thickening step there in order to reduce the load onto your solids handling. You don't want to oversize that for purely hydraulic needs there when you can thicken it up a little bit more. So we're just trying to make it as close to possible as you have with a conventional plant there. And then any sort of dewatering or digestion equipment will be fine, and I'll get you some data on that later here, Hans. But it performs similarly or better is really the mantra that we have with the solids handling on this. And again, that influent buffer, maybe or maybe not have it. Oh, that's the wrong button. You can also use primary clarification up front if you want it. But most people go with raw clarification or raw influent. I'm going to stop this real quick before I go into it. And then the other thing I want to point out is there's no secondary clarifier, which is what a flow through system would have. They would have all those selection basins and then a final basin to settle everything. So that is again with that batching process, we have all those selections occurring in there and we're settling at the same time, which we'll see coming up. So this animation is a batching process. We're running on a cycle time. So again, we can say it's 6 hours is fairly standard. And you're going to have a fill draw period, let's say 2 hours if it's a 3 basin system. Then we're going to have a react period. And then that very end is going to be your settle time with that waste discharge, which should be less than 30 minutes when you combine it all together, usually like 25, 20, depending how much you're wasting out. So let's get into that. So this is our reactor here. And it's one reactor per plant or for this animation here. It's circular, it can be rectangular. We're starting with a simultaneous fill draw phase. So as we're filling the reactor, we're filling it and coming up through a settled sludge blanket. So you can see that those arrows spread throughout the reactor floor because we have a distribution grid there. It's coming up through that sludge blanket and it's giving all those PAOs, they're eating up all that carbon. You can see it has VFA, volatile fatty acid uptake. And as it's doing that, it's cleaving off that orthophosphate. So it's the phosphorus release there. So you actually see your phosphorus concentration in the reactor increase during this phase. And so as we fill it, we're going to simultaneously decant through a series of fixed effluent weirs. So you can see there's no mixer in here and there's also no moving decanter. So we have a full hydraulic design with this that we do as well to ensure that we aren't going to get a breakthrough occurring or short circuiting of that influent getting to the top too quickly. And here's that water level correction. Notice we're dropping that water level about half a foot there. So it's a small amount of water, but it comes out pretty quickly. So that's why we have that small tank to equalize it before it goes back to the headworks. And we dropped that water level because our air blowers kicked on here. And you can see the diffusers at the bottom. And then any blower can, blowers are going to be site specific kind of based on the operators and engineers kind of experience and demands or wishes. But as you get oxygen into the system, you obviously get your nitrification. Then we're also going to get denitrification because we have that nice big granule there. This is where you're going to uptake all of your phosphorus. And then you're also obviously your carbon reduction as well. And then, as I said, there's no mixer. You get enough mixing energy just from the aeration system because the viscosity of the bulk liquid is a lot lower than conventional sludge because those solids are bound in the granule. And then the settle phase, blowers get shut off, pretty simple here. We're going to let it settle for about 15 minutes. And then we're opening that waste valve again. That's what we wasted that water level correction through. And there's another pipe that we don't have, we have it shaded out here, but that's running kind of across that center of the reactor that's pulling out that fluffy filamentous sludge there. So that's how we're deselecting for the filaments. And I really don't have too much of an issue with filaments, again, unless I'm in the startup phase where I'm still predominantly conventional. All right. Does anyone want to watch that again or go through it again or good to move forward? Okay. Mm-hmm.
Is there any possible reasoning? Thank you. These newfangled machines. Not to have your floating decanters in a system like this. I mean, why not utilize that?
So that is going to negate that plug flow. So how we filled this reactor was we filled the water to distribute across the entire reactor floor and come up at the same time. So with a traditional SBR where we do use a floating decanter, you don't have the plug flow operation. You just dump water in there and it's already mixed up around. What we're doing is with this controlled feed, that sludge blanket there, that's our biological selection that we need to granulate. So if we're feeding like this, where it's across the reactor floor and the water is coming up, that moving decanter, it wouldn't cover your reactor surface to evenly withdraw the water. Mm-hmm.
Even withdrawal.
Mm-hmm.
Making use of the space in the tank.
But it would be to localize that area there. So even like, again, with that water level correction and that sludge, that is one of the proprietary aspects of that is where your wasting elevation will be, and it's design specific. But that's going to be replacing that. But even that, we're designing that to ensure that the withdrawal of that sludge is somewhat equal throughout the reactor. So even with that influent grid, what I'm looking when I'm designing my influent grid, the hydraulics, is that when I have my water filling at point A, which is the entrance, and that furthest point being point Z, I want to make sure that whole grid's going to fill within a pretty similar time period. Obviously, the water takes longer to travel to point Z than it does point A. So I need to ensure that my piping is sized adequately to convey that water quickly enough to ensure that I'm not going to be too lopsided in my withdrawal there. All right, good questions, guys.
So at the time of diffuser maintenance, you have a sump in the tank and.
You can do, there's a lot of different ways you could do it. You don't need to have it, you can drop a sump in there. What I try to do is actually we'll settle everything and we'll try to decant as much as we can through that water level, the sludge grid. It's about halfway down. You can pull a good amount out and then you can pump out the rest. Just drop a sump pump in there. It's going to be, even some plants with their hydraulics, you could even send all your flow to another reactor. So we did have to take one reactor down, or will be at one plant, just due to, we just had a failure on one of our sludge launders. It happened, and it could have been an installation issue. Obviously, our mechanical team has reviewed all the drawings to ensure that we are adequately supported. In the future, it could be specifying to vendors, we'll specify where certain welds are made, but that's a reactor we'll need to take down, and we'll be able to get in there and kind of see. I'm kind of excited to see it too, though, just to see how things, good to get in there and see what's happened after a few years now that we've been running them. But should be a pretty easy process.
We do have a lot of grid, so we would have to see a grid removal system, because otherwise it would use the
Yeah, definitely. You want good screening up front for that diffuser grid. I mean, with the MBRs though, I mean, you need better screening for MBRs. And then a good grit removal system is recommended. We're again seeding that plant in Georgia. They had a huge failure of their grit system, so even getting sludge to seed their reactor has been a bit challenging, because we're trying to avoid grabbing that grit that's just settled to the bottom of their aeration basins. So yeah, it's not ideal to have in there, but you definitely want to have good headworks in there as well. And also, just, you don't want the grit in the system. It's not a beneficial solid to have. It doesn't have any biological, benefit. So you have a little bit of a layout here. This shows a standard 3-reactor system. And just so you guys have an idea of how large those ancillary basins are, this is that water level correction tank. And there's one sludge buffer per every 2 reactors. So, then blowers here. Barbara, you want me to go to the other screen real quick with the 3 reactors here? Here's that small water level correction tank in red. And then the 2 greens are sludge buffers. And the orange is just the blower pad. All right, moving into major advantages, really, I think kind of an advantages and operations kind of a thing to see how it all comes through. So when we compare different technologies, I'll focus on the MBR. Kind of when you're looking at a life cycle cost, your MBR is, usually your worst case scenario when let's say you're not assuming land acquisition costs come into play. So obviously, little footprint there. And that's really comes from the energy requirement. MBR is really your worst case option for energy. However, it gives you a very small footprint and very high quality effluent. So there are certainly drivers to pursue that. But the Nereda is going to have that same footprint here. We are also running at a very high mixed liquor concentration. MBRs, I think we design ours around 10 to 12,000 milligrams per liter, and the Nereda's at 8,000 milligrams per liter. However, you see more energy use on that side because their oxygen transfer efficiency is going to diminish as their mixed liquor concentration increases. So because they're that flocculent sludge, that aeration system has to work harder to get enough oxygen over to those bugs. Because again, it's hard having to fight through that viscosity within the liquid. We can run at that higher mixed liquor without seeing your oxygen transfer efficiency decrease, because we're not having to fight all that extra viscosity in there. And we've done that oxygen transfer efficiency testing at our demonstration reactor at least twice, and may actually do it a 3rd time, just because we get a lot of good data from that. And we have tons of data. We have about 1,200 SBRs out there, so we have a lot of data from those too. So
a lot of operators don't realize how the 2 can look at the transfer efficiency and
as you think that you can be control, your energy costs are going up, and that's a big thing. And that's with your MBRs, they are great and they have their place. But when you're looking at a bigger plant, again, when you're seeing those membrane, maintenance today, that definitely adds up on the actual work, and then even your energy costs too. And that brings us then to the OpEx side of things. It brings in your energy use. Membranes are your most energy intensive technology up there because of the pressure you need to get through those membranes. Bardenfo, the 5-stage Bardenfo system, again, that's where you have those multiple tanks. And Hans keeps bringing up the RAS lines here, because when you have those, like a 5-stage Bardenfo system with those multiple tanks, when you're looking to achieve lower carbon and phosphorus limits, what you need to do is actually return the sludge that you waste out. Some of that needs to be returned back to an earlier tank, so that you can get more carbon back into the system to keep facilitating that nitrogen removal and that nutrient reduction. So we're eliminating that big return line, and that's one thing, capital wise, footprint wise, that's gonna be a reduction there. Those are pretty big pipes. They go back, recycle back at about 3 to 5 Q, or 3 to 5 times your influent flow rate. So when I have that little water level correction, those sludge buffers, those are very small flows. So that's, you know, the RAS there. Then the chemical use, obviously there's no chemical with this to clean anything outside of, you know, your probes and, you know, an analyzer, but there's no chemical going into the system, and obviously to clean the membranes. So that's a big savings over the MDR, in terms of your OpEx, and then, but it has that footprint, save those footprint savings as well. And, all right. So I kind of explained all this, but I probably should have jumped ahead because pictures are so much easier. So here, Barbara, this is perfect. See how it's showing you these different tanks here? So that's what I mean by a batch, where it's all one tank. So you'll see plants as they get larger, especially, is they'll have multiple trains of these, you know, 2, 3, 4 of them to get more flow through. So with the Nereda or even an SBR, you're just doing a few tanks. And to me, it's less of a headache if one of your tanks goes down. You don't have to take a whole train potentially offline. And then so we eliminate those selector basins up front. Everything happens here. We're returning the RAS from your secondary, or we're eliminating that. We're eliminating the secondary, and you're also eliminating any returns from within that part or the biological process itself. Footprint savings. Was this someone asked about? We were looking at the footprint, I think, earlier, the acreage here. So this is that Wolf Creek, Alabama plant, the Redneck Riviera. So I'll start over here this time. This was their existing system. This is a one MGD ditch from the 90s, maybe late 90s. And these were 2 half MGD ditches that were nearing about 50 years. And these are their clarifiers. So this was only 2,000 million gallons per day, or yeah, 2 MGD. No, 2 MGD. Yeah, this is not Chicago. Stickney, we have one of the largest treatment plants in the world is in Chicago. It's 1 billion gallons a day. This is the new Aqua Nereda train, just to the left. So we'll do it over here too, guys. Here's your Nereda. Here's Headworks. Here's their blowers. Reactor 1, 2, 3, new control room. Here we have 2 of those sludge buffers, the water level correction tank, and a coagulation tank. They don't use the coag tank, but it's there for now. They just run through it. So you can see it's pretty small relative to the reactors. And it's just off the screen is actually a couple of filters that they use to polish up before UV. Footprint comparison though. So those ditches were 2 MGD. That should be average flow, excuse me. These are averages, but you can see that tankage was over 2 million gallons and it's over 2 acreage of footprint. The Nereda system comes in at 3.5 average, 6 max, although we could, if the plant can re-rate for 7, we'll give them 7 out of the Nereda. We can pass it. But as you can see, they're doing almost twice the flow in less volume, and you can see the acreage is just, the footprint's much lower.
You're cheating, that's not fair.
No, and they're designed to meet a TN of 5 and a TP of 1.5.
You can't compare a multi-stage.
Oh, to an oxidation ditch?
No. You're building a one system. If I build an oxidation ditch for 3.5, it wouldn't look like the picture on the right.
No. Well, and these were phased in. Those first 2 ditches.
That's an unfair comparison.
No. Well, I don't think it's that far off though. I don't think they can get down to half an acre like we can.
You can, but it wouldn't look as big as that.
No, it's not gonna, you can't run them. You can't do 3.5 MGD through it. You don't have the volume there. So they essentially, for 3.5 MGD in a ditch, they would have, even if you don't account for the spacing there, which you need some spacing between those trains, they still would have only been able to add on 1 more train at this site based on what they've done already. So that's, if it were a greenfield site, maybe it's a little different, but this isn't. They have to work in that space there. Other option, sure, could they have demoed this and built new ones? Maybe, but then they're losing treatment capacity and they can't do that while they keep the plant running. They couldn't take a whole line down because that takes up a third of their, or a quarter to a half of their flow. So it is, I see what you're saying there. No, this is not laid out ideally. But what would they have done here? They would have added another ditch and still not be able to meet their design needs. Cause we do see, they get tropical storms, so we do see high peaks up to about 6. And those ditches were losing sludge during overflows. They have 10 acreage of lagoons with 40-year-old sludge that's it's been sitting for decades, and that they've just had storm flow sitting there because the system wasn't able to process what they needed to. So now they've been desludging those lagoons, and they're sending as much as they can through this Nereda. I get returns. They don't have a flow measurement on that return line. It's either a quarter turn or a half turn of that valve. There's no actual flow measurement. So I know that sometimes coming in, I could have up to 25% of my flow, if not more, coming from those lagoons. And those lagoons, that supernatant has ammonia and phosphorus at about 100 milligrams per liter. So they're pounding it through this system that those oxidation ditches could not handle. So big benefits in doing this and what you're getting out of the Nereda versus the effluent quality out of those ditches. So that's even past just the footprint savings here.
So would they retrofit the entire plant on the Nereda side?
Yes.
Or is the other part still in operation?
They're using just this for storm storage right now.
Just storage.
Yeah, and it's not storage that's designed into our system. It's not an influent buffer like we talked about earlier. It's just discrete storage. And I don't know all the details on how they run every little thing at this plant, but I just know it's coming into my system. It's
So
Run for a while.
in the space that,
Mike, can you?
yeah. Okay, so in the space that they would have needed to add another oxidation ditch, which would have only been 1.5 MGD more, right? Nereda came in and did all 3.5 MGD. Right, so then they would have had 4 oxidation ditches, but I do understand what you're saying. If you just build one 3.5 MGD, it would still be a little bit bigger.
yeah.
That's what he
It
was
would still
saying.
be bigger.
But keep in mind that we replaced all of their flow plus an additional 1.5 million gallons with just that 3-tank.
Well, then there's no
Nereda.
redundancy with just the one ditch either. That it just
Right. Right.
there gives them a little more
Right.
flexibility.
It's a little confusing because it does say existing
It
on
does.
that one thing.
I know we talked about
yeah.
changing that
But
previous.
that existing is gone.
Yeah.
They just use the one for storage. So.
They'll eventually demo over here.
Yeah. that one.
They could potentially use, I don't think a full train in the future, but a lot of people have been retiring down there. So their flows, they're one of the plants that do run a little bit higher mixed liquor sometimes because they're a little bit closer to their design flows and loads. So yeah, they've been running almost 4 years now though. I lost my spot.
So
There
they
we go.
had, I'm guessing, their storm events. They had
Big time.
back in the day.
They've had some big storms.
Do they have salinity issues?
They used to. They still have, I don't have issues with my process, but they used to have, that was one of the reasons he sought out the Nereda was because it's supposed to handle salinity better. The Ringsend plant in Dublin, they did a year-long, I don't have pictures of the Ringsend plant, but it's beautiful. It's right on the Irish Sea. Again, the double-decker reactors, but there is zero room for I have not shown you the Whitefish, Montana ones yet. You hold your tongue on that one. But no, the Dublin plant, they are right on the water. There's no room to expand there. So that was a footprint savings. MBR insanely expensive for 150, 60 million gallons per day. But salinity intrusion is a big issue at that plant. And even with their SBRs, which were run well, would have a lot of issues with that. So that was one of the reasons that plant in particular, the work that they were doing then, which was still a pilot, was why Lee wanted this at his site, was because the salinity issues he was having. They have been working a lot on the I&I to solve that. Rockford, our plant's been working on a lot of improvements to the I&I issues we've been having over the years too. So it may not be as much of an issue now, but when we started up, it was. Yeah.
Are you going to get into that salinity business and its ramifications on your process more, or should we?
No, but we can definitely take notes on that. I don't have any hard data on it here, but we can just.
We don't have.
Yeah. Yeah, let me see if,
Brings up.
yeah, there, and again, I have not seen any issues from that on what we've been running so far. Trying to think who else could have, it's really just Alabama. The Kahului Airport takes on Motley
For years,
Airport
maybe.
ways, but that's not running for another
Yeah.
2 years, so,
So we have 30, 31, 32 pump stations, over 50% of them are flood.
okay.
And most of that one plane has all that one, and I believe has someone.
Yeah.
They're bracket.
So I can look into getting the hard numbers, because we have the numbers on that, so I'll see what we have available. I don't have, I try to have as many little handouts ready to go, but that's when I don't have anything nicely written up on, because we don't have too much of an issue here. But that ring send plant is a good one. So I'll look to see.
That's one of my.
Yeah, and that is, I don't have a picture here, which is bothering me, because it is right on the water, like you cannot.
We have seen fluoride as well.
Yeah.
Okay, no, that, good to know, but that is manageable. And I can see if there's anything I can benchmark that against versus what we have running out there.
There's any studies on the flow of highly saline water coming into the system.
What would you if it's an upset? I should have, yes, it has happened and it has been tested. I don't have anything right off the cuff though, but we can follow up with that. And we haven't done as much here, but I know internationally that was something, salinity was a big early question for them, especially Europe. Most of Europe is on a coastline, unlike here where you have a lot of center stuff there, or at least I should say most of what their market is going to be covering, obviously a lot, more disproportionate than what we have here. So I'll look into that for you. And I think there could be an academic paper on that one, but I just don't want to promise that that there is a published paper on that. Otherwise, I'll look for our international data to see what they might be able to give me. And I'll see actually if Wolf Creek has numbers. I don't get any of that from them. I don't know if they test it, but I will see what they might have. So I get in terms of what the effluent quality you can achieve or what we'll design for and guarantee, out of the Nereda can do about 1010 BOD TSS. Ammonia, we can actually do down to 0.5. We're fine guaranteeing that. I've seen, well, great performance on the nitrification side. TN, 3 milligrams per liter, and TP is 1 biologically. You can add chemical to the Nereda itself and get your 0.5. If we're looking to polish up even further, anything particulate related, you can do the cloth media. We've got the Aqua disc there. TP less than 0.1. We do have a couple of very aggressive sites in actually Alabama and Wisconsin that need to get very low TP limits. I think the lowest we have is 0.07. Is it 0.04?
I've used 0.04 in Alabama.
Yeah, Alabama. I mean, to the point that your measurement, your lab measurements have to be so precise that it's almost within a margin of error there. So, I don't think you guys need to do that well with your phosphorus here, but the polishing is nice. We have about half of our plants with filters and about half without. So it's kind of just site dependent. Most plants want it before. Most UV manufacturers will want it beforehand. My whitefish plant does go straight from Nereda to UV though, without any disc filters.
The Wolf Creek, is that discharge?
Yes, they to Wolf Creek. Yeah.
I just want to see that.
Yeah. Oh yeah. Yep. All of our plants do. You should be able to search them all up. All right, getting into how you actually run this more on the operations side. So I probably should have done the equipment list first now that I'm thinking about it. In terms of equipment within the reactors, all you have are those disc diffusers. The piping grids is not what we would call really equipment because you don't expect an operator to do anything to maintain it. What you do have on are the instruments. So we have a minimum of DO for your dissolved oxygen, pH, and then your ORP, pH and ORP, a little bit kind of similar to help us gauge our environment in the reactor. And then the final one that'll be standard is your TSS. So if you're looking at a pretty basic plant that really needs just BOD, TSS, maybe a higher ammonia limit, no no TN, no TP, we can run it just off a pretty basic set of instruments there. Just for good practice, you always want to have a certain amount of time for your aeration period, maybe 45 minutes to an hour for, a standard plant. So as you're running through that reactor, that react cycle, it's going to make sure you're running for a long enough period of time that the operator has specified. The operator will also specify a DO set point, usually 2 milligrams per liter for most of biological systems. And then we're also going to specify a pH stopping condition as well, because that's going to help ensure we've gotten enough nitrification. pH can be used as a surrogate for nitrification. And that's because that nitrification process eats up that alkalinity that comes in. And as that happens, your pH decreases. As you have more stringent effluent requirements, you can add on different instruments. Again, low ammonia, when we're looking for less than 1 milligram per liter, an ammonia probe is good. Nitrate probes, if you're looking, I forgot, I think it's less than 7 is what we recommend right now. I'll have to confirm that. And then phosphate for less than, I think, 1.5. So and you don't need all of them, it'll be site specific here, but as the operator, what that's going to happen is we run through these, we want to make sure that you're getting your timer, you're getting at least that adequate time in. You want to make sure then that you're hitting your DO, and it's also going to make sure that you're hitting that ammonia. And once it hits that, it's going to, and this is, I don't want to say dumbed down, but a little more basic here. It's going to stop the aeration. Your blowers are going to be on VFDs. It's going to slow it down pretty substantially. And as you start seeing your DO will decrease a bit, it'll ramp it back up. That's kind of a simplified way of explaining it, but those are the things that the operators can toggle and play around with in their system. It's pretty much, when we're doing startup, we've got it pretty much dialed in with them, and we, review this all together. But for some sites, especially with seasonality, you may want to make some changes. You may want to run, I guess for a really good example is the Wolcott plant in Kansas. Their ammonia limit in July and August is 0.6, and then I have it in 0.7, and it goes 1.1, and then in the winter it's 2.1. So twice a year, kind of in the spring and the fall, they go in and they change the ammonia setting in there. They want to target like 0.03 during the summer. They're pretty aggressive to hit that 0.6. Then they increase it up to about 1.5 during the winter so that they're sending less air into the system to save energy. And they're still emitting the ammonia they need. Justin, do you have any questions on that? Process resiliency, I hit on this a little bit. This was just some bench scale testing we did a few years ago with a low pH. And obviously as your pH drops, most biological systems want to be 6, 6.5 if you're looking for BNR there. You can see as your pH drops, obviously your ammonia removal decreases. And as we got it back to normal the day after, we saw the AGS recover pretty quickly. I really I think focusing on that Idaho Spring and some of the full scale, I would say, upsets we've had. Kind of another operations point here is how we manage peak flows. I mentioned earlier about improvements to the programming where the interim program that would just be run off the PLC is going to be able to respond to flow conditions more quickly. What the Nereda runs off is something called a Nereda controller that we provide the software structure and programming for that. And what it'll do is it'll take in that flow meter signal and it'll read it in on that controller and it'll say, well, I have a lot more flow coming in. And at my current cycle structure, I'm not going to be able to fit enough through during that fill period. So what I need to do is I'm going to shorten my cycle time up. And in this case, say from 4 hours to 3 hours. Where's my clicker? Oh. Well, we'll go on to the next one. This is a good one. So this is tough to tell here. I'll use this screen, guys, for now. This red line shows your level in the reactor. And this portion here, this longest portion is your general process depth. This is the depth when they do their sludge waste. And then they fill it back up where it's a little bit higher plateau. And then it drops again during that water level correction. And we're back to normal operation. And this is tough to read, but there's also a blue line here that's very faint that shows the flow. And you can see here, it's kind of low. It's about 1.5 MGD, but you see it jump up here. So they had a lot more flow coming in. So here the flow was pretty low, and then you can see it jump up pretty high here. But if we look, the cycle time between here and there is longer than between this little point and that point. So the cycle structure shortened up a bit to allow more flow to pass. And again, they get little freak storms down there, and the water goes away right away, and then so it'll lengthen back out. What you have in the controller structure is essentially, and this is something we designed for, it's kind of a hydraulic limit in terms of how much water you want, new influent you want into that reactor. You don't want to have so much that you're overwhelming the biology. Again, that food to mass ratio kind of a thing. At the same time, you don't want to have too little food to feed it. But this is just taking that onto a much shorter scale. We don't want to exceed that too drastically. So operators do not need to sit and wait for a storm to come. It'll be handled automatically. Already hit on this, inside the tank equipment versus outside the tank. Diffusers inside, outside. I went over the instruments. And again, that was the big change we made, was from ammonia analyzer standards to ammonia probes. Everything else is pretty standard here. Blowers are, flexible, whether it's centrifugal, turbo, hybrid. It's really going to be, dependent on the size of your system and any other restrictions you may have. Also already hit a little bit on how we start up. We're seeding with conventional activated sludge. And what we do is generally, you're going to gradually increase the hydraulic and organic load to it. We can start up at whatever your full flow is at the time. We just need to seed it appropriately. So when I'm looking at seeding, I'm looking at my food to mass again to make sure I'm within an appropriate range. So if you want to meet at your startup at, let's say you're at, 1 MGD, we'll seed it to ensure we can add a good food to mass ratio. The other option is you use less seed and you gradually send more flow to that system as that sludge increases and as we granulate. The granulation process does take, we say 3 months to be fully granulated, and that means that 70% of your mixed liquor concentration consists of those granules. So this was actually Wolf Creek. We started up in the middle of January. They were taking their first samples probably a week or two later, and were meeting their effluent needs then. And then they took a bit of time. It took them 6 weeks to divert their flow, although they were maybe about 2/3, 3/4 design flow back then. I'd say we took a little bit longer there. It was our first startup, and I think we were pretty conservative looking back now. I think the Wolcott plant was in about a month. And then you just really are focusing on granulation and then long-term operation at that point. When we're seeding a plant or starting up, we want to know what that seed sludge is, and be cognizant of your effluent requirements at startup, whether it was your existing permit, what the design objectives are, if there's going to be any sort of interim or lax permit during that startup phase. That's all going to kind of dictate how we're operating. Characterizing the seed sludge is important. If you seed with digester sludge, you can definitely expect a greater propensity for foaming and scum at startup. If you're taking CAS out of a well-run conventional system, you shouldn't have as many issues there. So that's something we try to, keep in mind and make people aware of.
So would we be operating our regular system to create the sludge, or how
So
do you meet your?
every plant is going to be started up differently.
Yeah.
So like Wolf Creek, they had an existing system there. And so they're not going to pull in sludge from a nearby community. They're going to use what they have, and they just pulled some and dumped it over into those reactors. Other plants are completely greenfield installations, and they do have to haul in sludge from a nearby plant. You're usually not looking at much. It can be maybe a dozen trucks or something. It really depends on each site and what your startup conditions are. So I'm not sure. I know you guys, it sounds like there's still a lot of ideas on what may happen here, whether it could be some retrofitting or existing site work or a greenfield site. So you guys can you're going to need something to treat, keep treatment occurring until the Nereda is up and running. So you could take sludge from that MBR, or you could go to a nearby community and grab sludge from them. You can use WAS or the digester sludge that's higher concentrated, so you need less of it. Just keeping in mind, it may take another couple of extra weeks to turn that over. Thank you.
She's halfway done, so I want to give her more.
Oh, we're getting there. And if you guys just let me know if we're doing okay on time here. All right. Is that clock working? I don't think it's moved. Now that I'm thinking about it.
No, I'm kidding.
You are at the beach.
It's 5 o'clock always here, right?
I'll have to leave.
Almost July.
Okay, and we might, Hans, if you want to follow up with me, and I'll give you my card and stuff. So yeah, starting it up. So yeah, Barbara, it's going to be site dependent. I can't tell you right now what you guys will do. It's going to depend on what your future, how you guys approach this. But we'll make it work either way. We've done a lot already, and then we have another. By the time you guys get something started up, we'll have another couple dozen in our portfolio, I think. But what we're going to be focusing on is maintaining a good food to mass ratio there, Hans. And again, kind of juggling our granulation target and our effluent objectives. So again, we start off at a higher settle time with that conventional activated sludge, and you just immediately start reducing that. Actually, when you do the wasting, I have my phone with me, I can pass it around, but we just put a little sample port off the waistline out of each reactor, or actually just the common waistline, whichever way it can be done. And all you do is the operator is going to head out during that waste phase, and the controller tells you when it will happen that day for which reactor. And they go out there and say it's 5 to 10 minutes long. They're going to open that sample port and collect some of that waste within a little beaker or a cup. They set it down, close the port, set it down. They're going to do another sample about halfway through, set it down, and they're going to open it a third time just at the very end of that waste discharge. And what they'll see is it's very full of solids at the beginning. It's a little bit less full of solids in the center, and at the end, it's clear. During that startup phase, I'm still going to have some solids at the end, and then it's going to clear up, and then I'm going to reduce my settle time a few minutes. It's going to be cloudy again, and then it's going to clear up. So that's what I'm doing through that startup phase, and that's what takes a good month or two to really get down to that 15 or 20 minutes as you're going through that granulation process. So you can see it by that. So even if you don't see granules right away, which you won't see them at first, within a few weeks, it'll take some time to really start to see them, but you'll know it's granulating as you're seeing that settle time come down. And as you run settleability tests, remember we saw that column where the two sludges were dropping. That's another sort of metric that operators will use to gauge SSV and SVIs. All right, information. I really look at this, Jeff and I were talking earlier, is that this is a transition from a more mechanical focus to a little more process focus. And Jeff, you laid it out really well that, something like you had a 5-stage bar info that you worked at, that's very biologically driven, how that functions. And you, of course, have some equipment on it, whereas your MBR certainly has a biological process, but it's also a really big mechanical component in keeping those membranes going. So in this case, with the Nereda, you want to have, there is obviously you have to keep pumps and blowers going, but the bigger focus is being proactive with your instrumentation maintenance, which should be into your SOP, scheduled out throughout the year. Obviously, if you are a bit late on it, that's okay, it happens. But it's kind of making that flip from going out and keeping your return pumps running or dealing with high flows to kind of making sure that your process trends look okay. So that's something we, discuss with operators. Because those who come from, again, like the Whitefish, Montana guys running a lagoon, all they cared about was that their chemical feed pump was going. They didn't have to do anything else there. Well, they also didn't have great effluent quality. They weren't meeting, nitrogen limits. They were spending tons of money on alum to hit that phosphorus. So it was a little bit of a transition. So they went through some wastewater classes, and I've been working with them a little bit longer than I have some of the other plants. But now I have operators there who go out and run an SBR or any sort of activated sludge plant, whereas beforehand they were new to it. So sampling and lab analysis, all I need will be what your permit requires long term. Those first few months going to be looking for a little extra data. Your sludge sampling is pretty similar, except we use coffee filter papers instead of lab filter papers, which is good because they're cheaper. But that sludge gets so heavy with those granules that we have a little bit different methodology in the lab there. I'm big into data organization. Again, some of these guys coming from a lagoon, they didn't really care what was happening. They just, gone with it. I like kind of seeing spreadsheets, so I help operators out with that when they're new to a little more advanced technology. And then communication. Ideally, during the construction phase and we're getting our equipment installed, you're going to have meetings with the contractor, the engineer, and all the involved parties. But after startup, it's going to be myself kind of meeting with the operators weekly, more of a one-on-one sort of a deal, and then bi-weekly and then monthly as they start feeling more comfortable with the system. With an SBR, we don't do that because most operators out there have some SBR experience or at least activated sludge. So with this, there's a little extra hand holding because we don't have operators who have run these in the US yet. And then finally, in terms of where are you? Come on. Did I lose it? Oh no. I just lost it. Oh, maybe that did it. Okay. Okay. It worked. It got us. We'll see if let's see. Oh, we're good. We're good. Thank you. Process management, pH, alkalinity, similar to other biological systems. Again, I'm focusing on a food to mass ratio, not a solids retention time. You keep an eye on that waste monitoring, like I said, and that's something that you should do maybe once a week on each reactor long term. Again, because your sludge yields are going to change as that carbon's coming in. You may be producing a little more sludge there. And then you'll adjust your settle time as necessary. So this was Wolf Creek, a month after starting up, 4 years ago about now. Thank you, Hans.
Yeah, my card.
Oh.
Oh, that's it. I would have noticed it right away outside.
She want the brush.
Like her card.
Yeah, do you want my card real quick, Hans? Sorry.
Sorry for interrupting you, Barbara.
Oh, no. Please. I'm glad you were.
I have a doctor's appointment at 5 in Milford and they're already called with
Oh my gosh.
Jeez.
I really
Thanks for
appreciate you coming in.
For me?
Yeah.
Yeah, that's true.
You're gonna miss the solids handling part, Hans. I know that's what you're
Yeah.
waiting for. I'll follow up with you on that. Make a note there. So anyways, what you see is this is what it starts to look like after operation, if you start up. And you can see it's tough to tell. It's still kind of liquidy there, but there are a bunch of these little specks. They're all granules. That's what it starts off at. So it's not very impressive. This is why you don't see these in our marketing photos. It doesn't look like much of anything. But give it another few weeks, and actually this one is pretty late here. It's all the way into that October. But you can see it looks like our demonstration reactor after 3 years. It's very well granulated, and you've got these nice big granules. Usually we stop measuring at a 2 millimeter sieve. I think our lab at Aqua will go up to 4, but yeah, so that's in well under a year, it's very much considered a mature plant. This is how that granulation concentration increased at startup. So, we start off with pretty much no granules. And this is all, of course, going to be contingent on your testing methods. And yeah, I think things were a little rough at first here. You shouldn't really have that high of a mass here. But what you see is a pretty rapid increase in that granulation. It looks like a little bit like a hockey stick. So I think we were a little bit slow here, I think just due to probably it being our first plant, but you can see how quickly it gets up there. It took about probably, about 5 months to get there. Most plants are about 3 months now that we've got some good experience with this. And this is another metric we use. It's called an SVI, a sludge volume index. You have it at 5 minutes and 30 minutes, and it's essentially just a settling ratio, the settleability in 5 versus 30 minutes. And essentially what this shows is that we get most of our settling done in the first 5 minutes, and there's very little that is occurring in those next 25. So that's like that side by side I showed where that conventional sample, it kept going and going. It needed all, 20 minutes plus to settle there. He just missed the solids handling. Oh my gosh. Oh, it just flew through everything there. I must have hit something. I'm just going to say that. Probably me. Okay. So just missed it. So I'll expect everyone to memorize this and repeat it to him. But the aerobic granular sludge, it does produce more EPS than a conventional system. And that's because I showed you, we have that graph of having all those PAOs in there. We have more of them. And that is concerning for a lot of people with solids handling experience because it's slimy and it can easily gum up some of the works there. However, even though we're dealing with the same biology with the granular sludge, we saw that graph where, you had our white, our yellow bugs, our green bugs, our pink bugs. This is, and I am not a biologist, is a alginate-like exopolysaccharide. I can pronounce it. I can't tell you the specifics of it in that, but essentially this is what the EPS flocks look like out of your activated sludge system under a microscope. This is what the EPS looks like from a granular sludge. It just looks like a tiny granule. So that sliminess that Hans is probably concerned about, or he actually might be concerned about the granules themselves. It doesn't have a negative impact on the process. On the digestion side, aerobically, and this is where I said earlier, we perform similarly or better than conventional activated sludge. The VSS destruction is similar. We're not making our sludge yield, the sludge that we produce and need to waste is similar as conventional sludge because it's the same biology. Anaerobically, we get a little more methane production, and that's because the most of what we're wasting out is very light and biodegradable. It's more that cellulose fibrous material. Long term, you do waste out some granules, though. That's how your system will just keep increasing your mixed liquor in there, and it'll be too much for your bugs to support. They won't have enough food coming in, and that's fine. Yeah.
More methane production, that means more odor problems?
This is specifically looking at anaerobic digestion. So the sludge that comes off the system and goes into solids handling, something needs to be done with that. Not all sites digest, some plants dewater, some plants just cart it off site. So that anaerobic digestion, when people are anaerobically digesting, it's usually a larger plant, they want more methane production because it's for energy. What it's called is cogeneration. They're producing their own energy at their plant. So that methane production is energy that their plant is using to run. So it's actually a positive, and it's not actually linked to the Nereda really in terms of odor. You definitely want to keep your digesters. You probably want to have an anaerobic digester covered, but that's actually a benefit there. The odor concerns with Nereda, it's not odorous at all. Odor concerns on a plant come up front before you start getting into your pre-treatment. It's in the primary area of the plant. In terms of wasting the granules, that does, like I said, happens long term. We need to keep that mixed liquor down. Sometimes you can't waste enough just through that little selective discharge of the flocculent material. So once a week, once every 2 weeks, it's site specific, they'll run a mixed discharge where they, instead of settling 15 minutes, they'll either open that waste valve right away, or they may settle 5 minutes and let more sludge out for a certain period of time. And that's fine. That's perfectly fine that we're doing that. I know people get worried about, even my operators, they don't like doing it because they're losing granules. I said, well, they're gonna be building more. You're fine. You're fine. It's okay to have a spectrum of sizes in there too. That's how it kind of works there. So yeah, I'll get with him and I'll send some papers on that too. On the dewatering side, this is what most sites will do. Maybe not all sites digest, but they'll either thicken or dewater. And you see a good reduction in your polymer use and or an increase in your dry solids production. The Wolcott, Kansas plant, they thicken on site using a rotary drum thickener. And they started that up maybe 4 months after the Nereda, a few months afterwards last year. And they started dosing it at, I want to say, 4 pounds per dry ton, because that's what they do at their other plants in the Kansas City area, their county. And it was thickening up to the point that their TWAS basins, the aeration system, couldn't keep up with it. It was just popping up some bubbles. It wasn't getting everything aerated there. So they just had to keep reducing the polymer use. And now they're pretty much between usually about 1/4 to 1/2 pound of pound per dry ton, which is a very low amount. Essentially, took them 1 year to use a whole chemical tote of that, which was very insignificant relative to their other installations. So we have data on that to share too. Unfortunately, we don't have tons of solids handling data from the US or even in general, just because operators don't always, you don't have to test it. It's not permitted for a lot of things. So It's the data that I have, but I'll send some stuff on that. Yeah.
Would you go back to that last slide?
Mm-hmm.
The 15 to 20%, is that?
Yeah.
At the,
That would be, yeah, in the cake there. And it should be, it's not percentage points, it's a percentage decrease there for that.
Now, you take a look at like your footprint or your footprint only takes into account the actual treatment process.
Yes.
The solids handling is totally separate. from the
Yes.
site.
Yes,
How-
correct.
How you know.
Because I'm not designing that either. I'm pretty much, I mean, and I'm not like we're operating in a vacuum, but that's what Aqua Aerobics is designing. And we'll tell the engineer and you guys what is coming out and what needs to be designed downstream, but we're relying on you to tell us what's coming into our system. But yeah, that's not coming in. So we're looking just at Nereda and our ancillary basins like the buffers and whatnot. So anything that is integral to the operation of our system. All right, so before I wrap up here, Barbara, did you want me to jump into that other presentation that I gave the installation update on? We can glance at a couple of those, or you want to open to more questions, look at your design?
I think look fine.
Okay, let me 1 second. Actually, do you mind sharing? We can put it on the screen too.
Oh.
Yeah, if you want to, Sharon, there should be a subfolder in the flash drive I put on there.
Well, they all have it in their package.
Okay.
Yep.
Well, we can just go through it that way if you guys would prefer. Otherwise, it is in there. In the Lewes, Delaware folder, the top, all the way at the top, Lewes, Delaware. You guys got your own special folder. And then, yep, perfect. Preliminary design, second one up. Perfect. Actually, maybe I should go over there since I'll have to scroll through it. I can talk through it with you guys. So, okay. I would jump on to page 5 of 14.
If I can first, Paul, let me just explain.
Yeah, please.
How we
Bill, go
came-
ahead, 'cause
yes.
I'm jumping into this project specific here.
Okay, in your questionnaire that you had sent to us under design parameters, it had an average daily flow of 1.75. And what Austin and I together to try to find out what we needed for the peak flow rate, not just the average. In our overall design, want to look at what the max month is because you have to treat that condition. So I was able to find the original specs for the MBR. And so what we did with the 1.75 for the membrane bioreactor specs, it said the system had to be capable of treating up to 1.2 times the average daily flow. So I took the 1.75 times 1.2, and that's how we came up with the 2.1. And then the max flow just scaled equivalently to what the MBR specs were on what flows had to be handled. So by no means are we locked into that. If you have something more, you feel is more accurate, we can, Paula can kick you out a new design and update the budget pricing very quickly.
Austin?
Paula won't be, another engineer will be, but I can
Okay.
tell her too.
Paula's department.
Yeah, the 1.2 I thought would be the if our average is 1.75, what do you think our peak is?
I have to go look. I wanna say under current circumstance on this, and Jeff's down there in the work study, what do you peak at, Jeff? I mean, you've probably seen.
Currently,
Yeah.
the highest I believe I've seen is 1.2, 1.3
At any given time,
in the last year,
I think I've
for
seen,
over a 24-hour period.
yeah. Not saying it can't do 1.8 through that plant.
That's the most that we've actually seen come through the plant in a 24-hour period.
So are you comfortable with this design summary, I guess is my question.
I think under this, like at the level we're at now, I think
Yeah, that's
fair.
fine.
I think we decide. I think this is fair. This is pretty much identical to what we had. I mean, I would expect,
Thanks.
Jeff just asked if this was for 2 or 3 reactors, so I did want to point out that this was for 2 reactors with that front equalization, that influent buffer. So your basin size here is about 420,000 million gallons per day. That's slightly larger than each reactor at Wolf Creek. So again, you guys are at the position where I do think you could do either or with 3 reactors as flow through or 2 plus the buffer. And you do have an operator here who could provide some input. You guys should definitely get theirs as well.
this is assumed that we have EQ storage on the front.
I would have to talk to see how this was actually designed with the design engineer, but I'm assuming whatever flow that you guys, I'm taking the flow you're giving us. It's kind of like Wolf Creek, that was that oxidation ditch storage. I don't know what they're doing with that. They're metering it in when they can. It's not what I'm designed to held up to that sizing or anything. So, yeah, whatever you guys are doing, just make sure that it's accurate to what you think we would be processing during your peak periods. And again, either way, with or without the buffer, it can be done 2 or 3, 2 with and then 3 without. Again, the exchange off with that, its footprint is actually going to be fairly similar overall. The influent buffer will slightly reduce the size of the reactors themselves, but you have that buffer there. So it ends up being quite similar, but keeping in mind that those reactors all have a lot of equipment piping in them. They each have their own instruments as well. So when you go to the 2 reactor system, you're eliminating that 3rd reactor of maintenance and equipment cost. But you're keeping in mind now, if you do bring a reactor down for maintenance, do you have enough redundancy with just running one reactor in the influent buffer? So that's something else to consider, how close you might be. So again, there's you guys are at that sweet spot where I could see it go either direction.
On here, we have now concentration, that doesn't put it in the filters out, or is that, this is with.
Yeah, about 5.
Okay.
So, 10, BOD, TSS without the filters, your TN will be the same, but the TP there, that
little-
hit 0.6, you would need chemical or filters.
Now also, we had increased flows on there, I put it, let's do that down, doing maintenance, I think, we're down to 1.
Yeah.
We had increased flows and we had reductions on the process. So instead of doing with that, down to 75 or something.
Yeah.
How would that affect?
So that would be something ensuring we have storage within, and that's something when we're doing our design, we'll run a redundant design to ensure that we're gonna cover you guys. It is, we probably don't wanna do it during, during hurricane season, but you can't always plan maintenance, so that's the other point, right? So,
What I'm saying, so the 5 and 5 is, that's really.
Could you come up to the,
oh yeah, he's asking some good questions
Yeah.
over here.
yeah,
So when we're looking at the limits with the filtration, you're saying 5 and 5. If we have the reduction, if we have increased flows with 1 tank down, and we had to reduce the hold time, how would that affect the effluent limits?
So we're still going to design this to meet the effluent that you need. If you have, even with a 2 reactor system, you obviously do have to take a reactor down.
Mhm.
And you have a little less flexibility then, but you do have the influent buffer to store that. So
Okay.
we know that reactors are going to come down. That is, every single plant will take them down eventually. Thank you for joining us. So what we're doing is we're going to ensure that we're going to run a redundant design when we're doing our design process here to ensure that we are adequately sized for those down periods. We don't recommend sizing it for 100% redundancy, but probably like a 50%, doing it at a lower flow time of the year. So the one benefit with the 2 reactors is that or 3 reactors is if when you do that maintenance, you have 2 to play with, but no buffer. So it's a little bit of a give and take there. You're never going to make anyone 100% happy with a plant design, but it is that buffer does give you a little more play,
Mhm.
especially you have play with it all the time. You have really more flexibility with your cycle structure when you have that buffer, because your fill draw times don't need to be back to back anymore. They can be a little more
And
spread out.
What kind of impact do you have on the effluent numbers when the fill draw times are reduced? Like what
No,
kind of
we're-
change are you seeing?
No,
if
we,
it's-
we should not see a significant reduction. When you have your storm flows come in, we're assuming that they're more dilute. If they're not, then, give us a peaking factor and we
Mhm.
will design our aeration system to meet that. But yep, that's how we'll address that. So we're still going to guarantee these at that higher flow as well.
Okay, and the phosphorus guarantee without the filtration would be at a 4.
No, that's your influent. The 4 is the influent there.
Okay,
So without filters, we can still do the 0.6, but we'll
Oh,
need,
okay,
we'll
okay.
need chemical, to guarantee that. So we can either do chemical or filters to hit that 0.6.
Okay.
And then with the chemical, or with the filters, obviously you polish all the particulate though with that, so.
Okay.
In terms of effort, maintenance, the O&M on the filters is pretty simple. I did actually have that in the presentation too, a bunch of filter stuff, but those are just workhorses. We've got a few thousand of those out there and.
This group is gonna see some of your dish filters on Thursday.
Oh, very nice. Oh, that's exciting then. So you'll get to see the disc filters. I think they're fantastic.
Newcastle County?
Yeah,
Berlin, okay, okay.
Berlin. Very, very slight enunciation, emphasis there. Berlin. That's funny. Yeah, so the disc filters polish it up a bit. Those have been around for 30 plus years now. They use a very high quality cloth. Just for a quick filter background, anyone can design a decent filter. It's really that cloth that actually does the filtering. The mechanics is one thing. So it looks like carpeting, but it's a truly engineered fabric. Going through the books we have in our library at Aqua, we actually have multiple books on fabric engineering, textile engineering, which I thought was pretty interesting. But we own the company that makes and manufactures the cloth. They're over in Switzerland. We actually bought out that filter company again 30 plus years ago. And so now we work, there are European arm, and we weave all of the cloth ourselves. Not us, there's weaving machines. That's like, we said, we don't hire a team of grandmothers to knit all of this. But it's high quality, polyester withstands chlorine, for cleanings or anything. Usually just some squirt of Dawn dish soap will be all you need, and you pop it in there and you run a few back washes. So they're pretty easy. And how the discs, the operators will tell you, the discs are arranged in, they're vertical and they're made of like 6 segments, and each segment just comes out with some, couple of bolts, and then the operator just lifts it off. It's 50 pounds, even dripping wet. So you don't need a big burly guy to do it. You can have pretty much anyone on your team climb in there. Nice to have someone outside that you just hand it off to. And it sounds cheap, but the cloth is really held on by Velcro, and it's just nicely lined up there. And you just unvelcro it, you dispose of that sock, and you put on the new one, and then tie it back on. So maintenance on those is super easy. I kind of like talking about them. It's been a while, and it's much more tangible. You can see what's happening with the filter.
What's your life expectancy? How long?
Oh, 7 to 10 years on tertiary. Yeah. So it should last a while. And that's what you see with the competitors out there, is that they're replacing cloth very frequently. It's not the most expensive thing, but if you're doing it twice as often as you should, it becomes a more expensive thing. And then like we talked about, the maintenance, doesn't take long to do, but it's one more thing you have to factor into your month.
So that's what we'll see in Berlin.
Yep.
Which system do they actually have?
Let's be honest.
Yeah,
That's good.
they've got enough. It's not awkward assessment.
Also in Middletown too.
Well, that's,
That's in Delaware.
So you show the buffer tank equipment layout, 29 feet by 92. How many gallons?
That is on page 4 of the design. And your influent gallon basin requirement you've got there is 285,310 gallons. I would not put all of these in stone, obviously, review it here. So that, that's half the size of one of the buffers. So you essentially, or excuse me, one of the basins. So you have essentially 2.5 of those basins. I can't tell you off the top of my head what this would look like with just 3 reactors. But would probably be, you'd have bigger reactors, or we'd do 3 of them actually, and they'd be a little bit smaller, but your overall reactor volume would be greater then. So like I said, we can have our design engineer do another mock design though. And the dimensions are flexible, guys, too. What we have written here, again, not set in stone. So like the reactor dimensions of 59 by 45 and a half, we don't have to do that. It's going to be dependent on what your site layout is. It's more the volume that we need. Now, this is, if there's a cost to this, that piping is designed specific to that reactor size. So that may shift a little bit, but in general, we can look at the other options there with the layouts. It doesn't have to be that dimension. This is the most ideal dimension though, based on how our hydraulic design works. There are constraints that can make it more cost effective if we use a certain ratio.
So these are like convenient standards.
Yeah. Oh, yeah. So this kind of this 18 by 14 there, I kind of like using I know it's in meters because it's a Dutch technology. We do a lot of the design in metric, which isn't the worst thing. But I'm looking at that as kind of a nice differentiator in terms of the placement that I need for some of the piping arrangements there. It gives you the most cost-effective approach. So that's usually what we try to offer. But again, site needs will override, in terms of any odd placement of reactors.
Yeah, we've been asked to look at the tightest footprint that we can come up with. So as you saw in the Wolf Creek, those are 3 individual circular concrete tanks. Using common wall concrete construction is your best, most economical from a construction cost, because now you have common walls, you minimize your piping, and you get a much tighter footprint.
And we'll keep the access in mind as well. You want to make sure you can access the equipment also when you're common walling. So that's something we make, we'll make sure of, and that we make sure the engineer is aware of too, that you can reach everything you need to for this. There's not much in there again, but to, even those instruments, making sure they're laid out nicely so that operators is not too condensed. Make sure you have wide enough walkways, which is no different than other sites there, but I think, operators always want more space and more room and stuff, but you can't always give it to them. So it's finding a happy middle ground.
So are you saying we need the filtration to meet the current effluent limits?
To meet 5.5, yes.
Yes.
BOD TSS, then that is any secondary process. We'll need that. I know you guys are used to having those membranes that gets you very, very low, probably lower than what you need. But most municipal plants will use secondary and then tertiary filters, either cloth or old sand filters was what was done years ago. So micro screens, and now cloth is the thing to go to. So that would be a difference for you guys. But again, is the energy expenditure and the additional maintenance on the membranes worth getting a 1 TSS when you don't need it? It's,
What would phosphorus be without chemical filter?
1 milligram per liter on the phosphorus without chemical or filters. That's what just the biological means only of removal.
But in regards to the filters, if you follow up with your visit to Berlin and right in the state of Delaware, Newcastle County, we have 2 12-disc Aqua disc filters. At the Delaware City, 2 4-disc Aqua disc filters. I think that's what's at Berlin, right? I'd have to check, but I think they're 4-disc.
How often do they have to be cleaned?
We have a continuous washing system.
I saw that. Is that all the-
Periodically, then she pointed out to take these wedges out and replace. them.
Yeah, the only time that I've really seen where you have to do something extra is if you have some kind of a biological upset, and they're not clarifiers in the tertiary sense of the way we're looking at them here. They're designed to filter. They're not designed to be a clarifier. If you have higher solids, say like we do with our Aqua Storm or Aqua Prime, where we're using it for clarifier, in lieu of a clarifier, it's, the tanks are a little bigger because they're designed to handle more solids. The tertiary filter, you shouldn't be having, the high solids unless it's an upset.
So if we had our filters, but we use the larger holes in the filters and use their technology for that, could that work?
What do you mean the larger holes in the?
But we've got membranes and they have different size holes in them.
No, this is a completely different unit process.
Yes.
And you have that then flow into this?
You wouldn't need to.
The membrane quality is higher than a filter.
I understand.
It should be.
I'm saying if you use the larger holes, right, there's different sizes that you can have in the. membranes.
No, the membrane MBR is still gonna be a higher quality than a filter. Yeah. Yeah. And I don't know the specifics on what you're designed for or anything, but this is still gonna be.
Because sometimes we'll use these filters in front of the.
Yeah, often they're used in front of membranes to polish them up. Nope, yeah, not a problem. And this is,
That's the answer I want.
and this is just, I had the animation loop here so you guys can see. I know you'll see them, but to explain the cleaning, here it is, or there it was. This is a solids removal at the bottom. What we do is we work with an outside inflow pattern so that heavy materials drop to the bottom of the tank and it's removed through a sludge or solids waste there. You can see the hoppers, make it nice and steep so the solids sink down. And then what they had before this was the backwashing, which is kind of like a vacuuming. And so you can see how they're up or they're vertical. And as the cloth gets clogged, what you'll see is that the reactor, the water level will increase, and that'll trigger the drive motor to kick on, and it'll rotate that center tube. And so the discs are moving, but what we're going to have is just only backwash 2 at a time. I'm a little bit ahead of the animation here, but you guys can kind of get a sense. So we saw the outside in where the heavy solids fell, the light solids get collected, the filtrates going through the center tube down to the effluent weir. And then at this point, that drive motor kicked on, and you can see their stationary backwash shoes there. And essentially, you're just sending the discs, they're just rotating around it. It takes about a minute to do a full rotation. And this is how they're backwashed. So this is something that will occur maybe every half an hour to an hour or so, depending on your solids load coming in. We open up that backwash valve. You do 2 at a time. They're all rotating, but we're only going to open the valve and to pull it out of 2 discs at a time.
It's one of the main reasons we do that post equalization. So we have a 2 minutes flow, no matter how fast it goes.
Given the size of our plant, how much would something like that cost?
I don't know off the top of my head. Did we send any pricing for that in the past, Bill?
I think we had it broken out, didn't we?
You might have. You have to check that email that y'all sent. But we probably provided you guys a cost, yeah, for 2 4-disc filters. I don't know what it is off the top of my head, but I think Bill probably emailed you with a number with the Nereda.
Yeah, if I'm not mistaken, the email to Barbara had a number for the Aqua Nereda system and then a separate number for the filters. Okay.
Aqua Nereda system, 2.8 million, and the filter system was 480 something thousand.
Yeah.
So you still got to put it in the
Yeah.
pipes and pumps and stuff.
Yeah, where you guys, it's cold enough to do it inside still, I think. Wolcott has it like that. Idaho Springs is submerged, yeah.
You're gonna want it
Yeah.
inside.
And I'm behind the ball, on this, but so when you guys looked at us having to have that technology, you looked at what your plant does.
Well, no, it's looking, not even my technology. You guys need 5.5 BOD TSS. No, that is not met with secondary. You need tertiary treatment. And that's what an MBR it's considered secondary, but that membrane is acting as tertiary treatment as well. Yep. Yep, so we knew that going into this, you would guys want the filters on the downstream. I can tell you that a filter plus Nereda should still be less work in O&M than one membrane system. So, and we design MBRs, we sell them. They have a fit. They are certainly applicable for certain applications. But for the cost that you can have, we can have the footprint savings with Nereda without the O&M of the membranes. Your quality is not as high as your MBRs is, but do you need that stringent of effluent? And most municipal applications do not. If they started requiring membranes on every municipal plant, man, they better start shelling out the money from the government to get that low.
How often do you have to go physically on these filters?
Well, that was the other question. I don't know exactly how I would definitely ask the operators to see their opinion on it. I don't know, maybe even Tom, Bill, you guys have some more input. How frequently the filters are cleaned? Haven't talked to a lot of operators on it.
I
but-
only see it done in, say, an upset condition where something happened upstream and
Yeah.
it got hit with high mixed liquor.
And then it-
Now with the Aqua Prime, that's a little different application, but on a Aqua disc, standard Aqua disc.
I think the most I've heard is they might drain it and wash it down maybe once a year if they're really stringent on cleaning, and
For
that's what they have.
housekeeping?
redone.
Yeah,
Yeah,
I've seen that,
housekeeping. I think
sure.
it's more of a housekeeping
Mhm.
thing. But the actual cleaning shouldn't be frequent by any means. And you can
The-
tell when you need it. You can tell.
Detergent has only been used that I remember on applications where something happened with the treatment plant process upstream. They got a lot of grease or something that fouled the cloth.
Then chlorine cleanings, I mentioned that being chlorine resistant. That's really targeting the southeast. We do a lot of work in Florida, and obviously algae is a bigger concern down there.
On a lagoon application, yeah, Mark, you've done a few of those.
They don't cover their filters down south most of the time because they have like a roof over it. A lot of them are, some of them aren't covered at all. A lot of them aren't because they don't need it because it's warm. But, again, it's kind of the maintenance that comes along with that, but they get the more algae growth then. So not as much of a concern up here. Barbara, I know you had a number of questions on that email, so I don't know if we hit all of them, but
Well, there were two. The one, I've raised, I guess, if you want us to change those numbers,
oh, yes, definitely.
are you good with those numbers for now?
Austin was good.
Okay, and then the other thing, you had mentioned some photographs.
Yeah.
None of us three saw any photographs, so I'm not sure where those are, but what would be more important, and I did mention to Austin, is if he sends us, and he said he'll do that, the site plan of the existing plant with the hydraulic profile, then we can look at what we've done here and we can see where you have room and basically do like a drop-in kind of sketch footprint to show you where it could go.
That's really,
Yes.
is there enough room on that site? And
I don't
Yeah.
do the design work on this, so
Yeah.
I'm not as familiar as the background, what you're driving at, but if the goal is to use that existing plot of land or what you have, then yeah, the drawings will be integral and we can hopefully just estimate the
Yeah,
sizing there.
You'll find that some things will need to be removed, while something new placed here while this is being operated. There's gonna be a lot of that. There's not just an open space like we see in that one
Okay.
video.
Yeah.
One show that you had of the
Yeah.
oxidation ditches.
They had that nice
Open
section.
area. This is gonna be, take this down, put it here, and keep this
So
running.
that'll be
Yes,
something, yeah.
Austin had some
Yeah.
very good ideas. Yes.
Do this,
It was good to go through the tour with Austin. He pointed out a lot and yes. So with the site plan and the hydraulic profile, I think we can give you, a good idea.
questions from the public? Have anyone online with questions? Any more questions?
They'll come flooding in as soon as we leave.
Yes, right, of course. Um. Lead time,
Oh, lead times.
design and build, if we decide to go with this, just give us some idea. And then chemicals use,
Let's do the chemicals first, because that's so much easier for me.
Okay.
Chemical use should be fairly non-existent. So no polymer, right? Well, you know, we should, assuming that kind of walking through the plant, looking at the TN and TP objectives and the numbers, you should not need, you may or may not have the micro C for the supplemental carbon, because you do have a TN of 5. If you guys drop, your influent carbon drops low. You may want that available. Based on what the numbers are here, you shouldn't need to use any of it though. So that should be good. In terms of your metal salts, or like alum or ferric for phosphorus removal, like we discussed, you guys can get that all through the filters, or you can use chemical. So we can do either or in that case. If you have the filters, no chemical, no filters, we'll use chemical instead. And then like we talked about, I'm not adding polymer into the reactor, like Hans brought that up. That's not happening. I'm not dosing anything else other than potentially the alum for the phosphorus or the additional carbon for low TN if you guys are deficient. The only other thing would be the thickening, the solids handling any polymer downstream. But those, as we saw, the data shows that you should be using significantly less. And we can maybe help with some estimates on that based on some of the data I have and what they've seen overseas as well. So compared to a membrane, it will be significantly less because they don't have that cleaning going on, the chemical cleanings. Oh, and the other question was the lead times. Tom, 16 to 20 weeks right now for no, submittals right now are, do not quote me on this. We will get you more updated numbers. I believe submittals right now are about 10 weeks for the Nereda. Thank you. And then lead times on equipment from when we get the PO to when we can deliver it. As of right now, the longest lead time is at, I think, about 30 weeks for control panels. And that's exclusive, and that's just been how things have been since COVID. That lead time is shortening as we're coming out of this and we're getting more IO cards in, which has just been gradually improving. The rest of the equipment lead times, I think, are about 14 to 16 weeks. So maybe go with 16 for right now. And I could be a couple of weeks short on that. So I think it's fairly standard. And obviously, again, the only thing that has us antsy right now these days are those control panels. But any moment we hear that there's an IO available, we're buying it. I think we went to the black market for a bit during some of the dark days of COVID.
Are there specific contractors that need to?
No, we can work with anyone. The Kahului Airport project is actually with a contractor who really just works in pavement and roadways and whatnot. So this has been a little a bit of a stretch for them, but they're doing fine with it. So anyone who's worked with wastewater in the past should be fine. We've worked with a number. I don't think anyone in particular is really latched on, but there've been, different contractors throughout the country. They can be big national firms, small local firms is fine too. And obviously we'll provide just a little maybe extra support with that too. We know that there's, a lot of them have put up SVRs, but there's still some nuances that they're not sure about with the Nereda.
O&M.
Yes, that came with the design as well. I think there's one for the filters and the Nereda system separately.
Back to us about affinity.
Yes, so I have written down here salinity issues, solids handling info as well. I will send along that selection mechanisms paper. Hans might be interested in it. Is there anything else you guys can think of at the moment? Or shoot us an email anytime will be fine. I'll be traveling here for the rest of the week, so I don't know if I'll get you guys the things right away here, but the next couple of nights I'll pull it together for you.
Anyone else? Mark?
Oh, I appreciate you guys getting such a group together. This has felt very professional in here presenting. This is great. No, you guys had really great questions, so you're very well informed. Not everyone goes through this level of, I think, review and evaluation at times, so. Wastewater is important. Not everybody realizes how integral it is.
It is around here.
Good. Thank you. Next one.
Hey, and it is.
Okay, thank you. Does the team want to talk afterwards or,
If we have time, I'd like to.
and then we have to leave it open, but we can let you guys go.
I don't know that we have it on the agenda,
Ah, okay.
so.
But it's not an executive session,
Right.
but it's not.
Correct.
Part of our,
Mhm. I mean, it just says presentation, so. Mhm.
Are you going to run a show this week?
We're visiting a couple of engineers. I don't think we've had someone dedicated out from Aquarobics out here since we came on with the technology, so, yeah. I'm visiting in Philadelphia as well, so it's the timing. Worked out well.
It's more fun than that.
That and grandkids.
Yeah.
okay, well, I guess since it's not on the agenda, we'll have to defer until our November meeting of the committee. And perhaps, Jeff, we can get your feedback at that meeting too.
Yeah.
At least ours. Sumner won't. I goofed up. We have to have a sub forum.
Yeah, motion to adjourn.
Yeah, yes. Can we? Yes.
Yeah.
Motion to adjourn, anyone? Second? Okay. All in favor? Aye.